Hey there, reality enthusiasts. Buckle up because today we're about to completely shatter everything you thought you knew about existence itself. And I'm not talking about some philosophical mumbo-jumbo. I'm talking about cold, hard science that's basically screaming at us that the universe is running the greatest con job in history. Your eyes? Liars? Your brain? A professional deceiver. That solid chair you're sitting on right now? Mostly empty space playing dress-up as furniture. Welcome to the rabbit hole, folks, and spoiler alert, it goes way deeper than you ever imagined. We're diving into quantum mechanics that refuse to let particles exist properly, fields that make up everything while being completely invisible, and the uncomfortable possibility that you might be living in what's essentially the universe's version of The Truman Show. Oh, and dark matter. Yeah, that's basically the cosmic equivalent of 404-era reality not found, taking up 95% of existence. Fun times. This isn't your average space is big and cool video. This is the universe exposing its own magic tricks, and honestly, it's both terrifying and absolutely mind-blowing. So before we start questioning literally everything, smash that like button if you're ready to have your existential crisis for the day, and drop a comment. What city are you watching from? I want to know where all my fellow reality doubters are tuning in from across this possibly simulated globe. Let's get weird. So here's the thing that nobody really wants to admit. We trust our senses completely. You look at a tree, you assume there's actually a tree there. You hear a sound, you believe something made that sound. You touch a wall, and boom, solid wall, case closed. Except here's the uncomfortable truth that modern neuroscience and evolutionary biology have been screaming at us for decades now. Your senses are absolutely terrible at showing you reality. Like, embarrassingly bad. They're not windows into the true nature of the universe. They're more like those cheap Instagram filters that make everything look better than it actually is. Except in this case, they're making everything look simpler, safer, and way more solid than it has any right to be. Let's start with your eyes, those supposedly reliable organs you're using right now to read this. You think you're seeing reality? Think again. The human eye can detect a pathetically narrow slice of the electromagnetic spectrum. We're talking about wavelengths between roughly 380 and 740 nanometers. That's it. That's your visual world. Now, the electromagnetic spectrum itself stretches from radio waves with wavelengths measured in kilometers all the way down to gamma rays smaller than atoms. We're seeing maybe, and I'm being generous here, about 0.0035% of what's actually out there. Congratulations. Your eyes are functioning at a level that would get you fired from literally any job that requires attention to detail. Imagine if your phone only displayed 0.0035% of your text messages. You'd throw it in the trash and demand a refund. But somehow we're supposed to trust that these biological cameras are giving us the full picture of reality. Not likely. And it gets worse, because even within that tiny window we can see, our brains are actively lying to us about what's happening. You know that thing where you look at something and it seems like a continuous stable image? Total fabrication. Your eyes are actually making these rapid movements called saccades, little jerks happening 3 to 4 times every second, and during those movements, you're essentially blind. Your brain just fills in the gaps with whatever it thinks should be there, which is absolutely wild when you think about it. It's like watching a movie where every third frame is missing, but your brain is such a smooth operator that it just makes up those frames on the fly and convinces you the film was perfect all along. We're not seeing reality. We're seeing reality plus your brain's best guess about what should be filling in the blanks, which unfortunately isn't quite the same thing. But wait, there's more, because evolution really went all in on the whole good enough is good enough philosophy. Take colour, for instance. You look at a red apple and think, ah yes, redness, a fundamental property of that apple. Wrong. That apple isn't red. Redness doesn't exist out there in the world. It's a sensation your brain creates when certain wavelengths of light hit your retina. Dogs see a completely different version of that apple. Mantis shrimp, which have 16 types of colour receptors compared to our pathetic 3, are basically looking at a psychedelic rave version of reality that we can't even begin to imagine. They're seeing colours that don't have names, can't have names, because we literally lack the hardware to process them. It's like trying to explain what Wi-Fi looks like to someone from the 1800s, except we're the people from the 1800s, and mantis shrimp are living in the future. Not exactly a confidence booster for Team Human perception. Now let's talk about hearing, because oh boy, this is another masterclass in evolutionary corner cutting. Humans can hear frequencies between about 20 and 20,000 Hz, and that upper limit drops as you age naturally, because why should anything about this system work reliably? Meanwhile, elephants are communicating in infrasound below 20 Hz, having entire conversations we can't even detect. Bats and dolphins are echolocating with ultrasound above 20,000 Hz, essentially seeing with sound in a way that's completely invisible to us. There's this whole acoustic universe happening all around you right now. Animal communications, structural vibrations, atmospheric sounds, and you're just sitting there completely oblivious like someone trying to follow a conversation while wearing noise-cancelling headphones. The world is absolutely packed with sounds you'll never hear, which means there's an entire dimension of reality that just doesn't exist for you. Sweet dreams with that thought. And here's where it gets really interesting, in a kind of existentially terrifying way. Your brain isn't even bothering to process most of the information your senses do manage to collect. Cognitive scientists have determined that your brain filters out approximately 99% of the sensory input it receives. Think about that for a second. 99%. Your brain is receiving this massive flood of data from your eyes, ears, skin, nose, tongue, and it's just going, nah, don't need most of this, let's just focus on the highlights. It's like having a security camera system that only records 1% of what happens and deletes everything else, then expecting that to give you a complete picture of events. Good luck solving any crimes with that setup. Your brain is basically running the world's most aggressive spam filter, except it's filtering out actual reality and leaving you with whatever simplified version it thinks you need to function. So why would evolution do this to us? Why create these incredibly limited, highly filtered, questionably accurate sensory systems? Because, and this is the kicker, evolution doesn't care about truth. Not even a little bit. Evolution cares about one thing and one thing only: survival long enough to reproduce. That's it. That's the entire mission statement. Truth is a luxury, and evolution is running on a tight budget here. If seeing the full spectrum of electromagnetic radiation would have helped our ancestors avoid being eaten by predators, we'd have it, but it didn't, so we don't. If processing 100% of sensory information made us better at finding food and making babies, evolution would have given us bigger brains to handle it. But processing all that data takes energy, and energy was scarce in the ancestral environment, so instead we got these efficient little perception machines that give us just enough information to survive and absolutely nothing more. Think of it this way: evolution didn't design your senses to be scientific instruments revealing objective reality. It designed them to be a user interface, like the desktop on your computer. When you click on an icon, you're not actually interacting with the raw code and electrical signals inside your computer. You're interacting with a simplified graphical representation that makes the system usable. Nobody needs to see the actual machine code to write an email, and our ancestors didn't need to see quantum fields and electromagnetic waves to avoid getting eaten by large cats. The user interface metaphor is perfect here, except in our case, we can't exit the interface. We're stuck in it, forever clicking on icons and thinking they're the actual reality, when really we're just interacting with evolution's extremely simplified version of events, designed for maximum survival efficiency. Donald Hoffman, a cognitive scientist who spent his career studying perception, has this fantastic and deeply unsettling theory he calls the interface theory of perception. His research suggests that natural selection has specifically tuned our perceptions to hide reality from us, because organisms that see reality as it actually is get outcompeted by organisms that see fitness payoffs instead. He uses this great example. Imagine you're thirsty in the desert and you see a water icon on your desktop, in the world. That icon doesn't look anything like actual water molecules, doesn't represent the true quantum mechanical reality of H2O. But it tells you exactly what you need to know for survival. There's something drinkable over there. Evolution trained us to see fitness payoffs, food, water, mates, threats, not underlying reality. Truth literally lost the evolutionary race to usefulness, which is not great news if you're interested in actually understanding the universe. And here's another fun wrinkle. Our perceptions aren't just limited and filtered, they're actively constructed by our brains to match our expectations. There are all these cognitive biases and perceptual shortcuts that basically mean we see what we expect to see, not necessarily what's actually there. The famous invisible gorilla experiment demonstrated this perfectly. People watching a video and counting basketball passes completely missed a person in a gorilla suit, walking right through the scene because they weren't expecting it. Your brain decided, nope, gorillas don't belong in basketball games, filtering that out. This happens constantly, every day, with everything you perceive. Your brain has this running model of how the world should work, and it adjusts your perceptions to match that model, which is great for consistency, but terrible for accuracy. We're not actually seeing what's there. We're seeing what our brain's internal model predicts should be there, updated occasionally when the sensory evidence gets too loud to ignore. Consider temperature for a moment, something that feels incredibly direct and objective. You touch something cold, it's cold, right? Except that's not what's happening at all. There's no such thing as cold. There's only the absence of heat, which is really just molecular motion, and you're not even detecting that directly. You're detecting the rate of heat transfer between your skin and the object, filtered through thermoreceptors that give you a wildly relative sense of temperature based on what your skin was previously touching. Put one hand in ice water and one hand in hot water, then put both in lukewarm water. They'll report completely different temperatures for the same water. Your senses aren't measuring objective reality. They're giving you context-dependent relative approximations that work well enough for survival, but fail spectacularly at objective truth. It's like trying to use a rubber ruler to measure things. Sure, you'll get numbers, but those numbers are going to be pretty meaningless. Now let's talk about the other senses briefly, because they're all running the same scam in different ways. Smell. You're detecting volatile molecules, sure, but only certain ones in certain concentrations, filtered through a genetic lottery of which olfactory receptors you happen to inherit. Dogs have about 300 million olfactory receptors compared to our measly 5 or 6 million, which means they're basically living in an entirely different sensory universe, where smell carries vastly more information than it does for us. For them, smell is what vision is for us, the primary way of understanding the world. We're effectively smell blind compared to them, stumbling through a world full of chemical information we can't detect. Taste, even more limited, basically just 5 or 6 categories depending on how you count them, with huge individual variation based on genetics. Savory doesn't exist as a fundamental property of food, any more than red exists as a property of apples. It's all just chemical interactions that your brain interprets in weirdly specific and limited ways. And touch, oh touch, that supposedly most direct of senses. You think you're feeling the actual texture of things? You're not. You're feeling the electrical repulsion between the electrons in your fingers and the electrons in the object, which never actually touch, because matter is mostly empty space held together by forces. At the quantum level, touch doesn't exist. It's just electromagnetic force fields interacting. But evolution thought, you know what? Let's not burden them with that knowledge. Let's just give them the sensation of solidity so they don't try to walk through walls. Solid objects are a user interface shortcut for strong electromagnetic repulsion that will stop you from moving in this direction. Congratulations, you're feeling a force field and interpreting it as reality, which is simultaneously cool and deeply weird. What really drives this home is when you look at other animals and realize just how arbitrary our sensory setup is. Echolocating bats are essentially seeing geometry through sound waves, experiencing space in a way we can't imagine. Sharks can detect electromagnetic fields with their ampullae of Lorenzini, picking up the tiny electrical signals from muscle movements of nearby fish. Pit vipers have infrared sensors that let them see heat signatures in total darkness. Migratory birds can detect Earth's magnetic field and use it for navigation. These aren't science fiction superpowers, they're just different sensory modalities that evolution stumbled upon and said, sure, why not? If humans had evolved in different environmental pressures, we might have completely different senses, might be experiencing a totally different slice of reality, and we'd be just as convinced that our version was the complete and accurate one. The thing is, we can't even imagine what we're missing, because imagining requires having some framework for understanding, and we simply don't have the framework for sensory modalities we've never experienced. It's like the classic thought experiment about trying to explain colour to someone who's been blind from birth. There's no reference point, no way to translate that experience into their existing sensory framework. We're all in that position with respect to the vast majority of reality. There could be entire categories of phenomena, entire dimensions of experience, whole aspects of the universe's structure that we lack the sensory equipment to detect, and therefore lack even the conceptual framework to imagine. We're walking around convinced we've got a pretty good handle on reality when we might be missing 99.9% of what's actually out there, and we can't even know what we're missing because we can't detect it in the first place. Here's the really unsettling part though. This isn't a bug, it's a feature. Evolution did exactly what it was supposed to do. It created sensory systems that maximize survival, not truth. And those systems work fantastically well for keeping us alive and reproducing, which is why we're here having this conversation. The problem is that we've developed this weird tendency as a species to assume our perceptions are showing us objective reality, when really they're showing us a highly curated, heavily filtered, extremely simplified version of reality specifically, optimized for survival in the African savanna about 200,000 years ago. We're trying to understand quantum mechanics and cosmology with sensory equipment designed for avoiding lions and finding berries. It's like trying to run advanced scientific computing on a calculator from the 1970s. Technically possible with enough workarounds, but not exactly what the hardware was built for. So what does all this mean for our understanding of the universe? It means we can't trust our intuitions. It means that when physics tells us things that seem completely insane and contradictory to our everyday experience, like particles being in two places at once, or time being relative, or the universe being mostly empty space, we can't just dismiss that because it doesn't match what our senses tell us. Our senses were never designed to reveal that level of reality. They were designed to show us a useful fiction, an evolutionary interface that sacrifices truth for survival. The real universe, the actual underlying reality, is under no obligation whatsoever to match our intuitive understanding of how things should work, because our intuitions are based on a user interface, not on the underlying code. This is why science is so important and so difficult. We're trying to peer behind the interface, to understand the actual mechanisms driving reality, using tools that evolved specifically to hide those mechanisms from us. We're essentially hacking our own perceptual systems, using mathematics and instruments and experiments to detect things our senses can't show us, to build models of reality that contradict our direct experience. And every time we succeed, every time we discover something new about how the universe actually works, it's another piece of evidence that our everyday perception is not showing us the truth. We're not seeing reality, we're seeing reality's greatest hits, the simplified version for general audiences, the user-friendly interface that hides all the complicated stuff under the hood. The universe isn't necessarily what it seems. Actually, scratch that. The universe is definitely not what it seems, and modern physics has spent the last century proving that over and over again. Our senses are not reliable witnesses to reality. Their evolution's compromise between accuracy and efficiency won that battle decisively. We're living in a perceptual bubble, experiencing a carefully constructed simulation of reality that evolution built specifically to keep us alive, not to reveal truth. And that's just the beginning of how deep this deception goes, because if our senses are lying to us about basic things like colour and solidity and time, what else are they hiding? What other fundamental assumptions about reality are built on the shaky foundation of perceptions that were never designed to be accurate in the first place? Turns out the answer to that question gets significantly weirder, and we're just getting started. Now that we've established your senses are basically running a scam on you, let's dive into where things get truly bonkers. Because it turns out the problem isn't just that our perception is limited. The problem is that the stuff we're trying to perceive doesn't even exist in the way we think it does. Welcome to quantum mechanics, where particles have apparently read the manual on how reality should work and then promptly thrown it in the trash while laughing maniacally. Here's the deal. You think matter is made of tiny solid particles, right? Like microscopic billiard balls bouncing around. Yeah, no, not even close. That's what scientists thought too, back when everyone was naive and optimistic and believed the universe played by sensible rules. Then they started actually looking at these particles, running experiments, and discovered something absolutely horrifying. Particles don't exist as definite objects until you look at them. And I don't mean that in some philosophical if a tree falls in the forest kind of way. I mean in a literal, mathematical, experimentally verified way that makes physicists want to lie down and question their life choices. Let's talk about electrons, because electrons are where this whole nightmare really started. You've probably got this mental image of an electron as a tiny ball of negative charge, orbiting around an atomic nucleus like a planet around the sun. Cute. Wrong, but cute. Here's what an electron actually is before you measure it. Nothing. Well, not nothing exactly. More like everywhere and nowhere simultaneously, which is somehow worse than nothing. An electron doesn't have a location. It has a probability distribution, which is physics speak for we have absolutely no idea where it is, but we can tell you the odds of finding it in various places if you bother to look. It's like if your car wasn't parked in any specific spot until you went to the parking lot, at which point the universe would randomly decide where it had been all along based on a cosmic dice roll. Not exactly confidence-inspiring for your morning commute. This isn't speculation or philosophy. This is mathematics describing reality with an accuracy that's frankly disturbing. The Schrödinger equation, which governs quantum mechanics, describes electrons as wave functions, these mathematical probability clouds smeared across space. The electron isn't at point A or point B. It's in a superposition of being at all possible points simultaneously, with different probabilities for each location. And here's the kicker that makes this especially ridiculous. The moment you measure where the electron is, the wave function collapses and the electron suddenly decides to actually exist in one specific place. Before measurement, it's a ghost spread across reality. After measurement, it's a definite particle with a definite location. The act of looking at it literally changes what it is, which is the kind of behavior you'd expect from a glitchy video game, not from fundamental reality. Now let's talk about the double slit experiment, because this is where quantum mechanics goes from weird to I need to sit down and possibly cry a little. This experiment has been done thousands of times with increasingly sophisticated equipment, and it keeps giving the same mind-bending results, much to everyone's distress. Here's the setup. You shoot particles, electrons, photons, whatever, at a barrier with two slits in it. Behind the barrier, you've got a screen that detects where the particles land. Simple enough, right? If particles are particles, little solid things, they should go through one slit or the other and make two distinct bands on the screen, like if you threw baseballs through two windows. That's what common sense predicts, and common sense is about to get absolutely demolished. What actually happens is you get an interference pattern, multiple bands of particles creating light and dark stripes on the screen. This is the signature of waves interfering with each other, waves going through both slits simultaneously, and then overlapping on the other side. But wait, you're shooting individual particles. You can literally send them one at a time, waiting seconds between each particle, and you still get the interference pattern building up over time. Each individual particle is somehow going through both slits at once and interfering with itself, which is completely insane. It's like if you threw a baseball and it somehow split into a wave, passed through two windows simultaneously, reformed itself on the other side, and then landed in a spot determined by how its two paths interfered with each other. Baseballs don't do that, unfortunately, because reality decided that the rules for big things and small things should be completely different just to mess with us. But here's where it gets even weirder, in case you thought we'd hit peak weird already. If you try to observe which slit the particle goes through, if you put a detector at the slits to see which path the particle takes, the interference pattern disappears. Suddenly you get two bands, like particles should make. The act of measurement changes the result. The particle knows you're watching and decides to behave like a proper particle, instead of doing its wave thing. This isn't anthropomorphizing. The math and experiments consistently show that measurement fundamentally alters the system. Before observation, the particle exists in a superposition of going through both slits. After observation, it went through one slit. The particle's past literally depends on whether you measured it, which is the kind of time-bending nonsense that would get you kicked out of a philosophy seminar for being too absurd, except it's actually how the universe works. Now, scientists being scientists, they thought maybe they could outsmart the universe. They designed what's called a delayed choice experiment, where you decide whether to measure which path the particle took after it's already gone through the slits, but before it hits the detector screen. Surely the particle already went through one slit or both, and your later decision can't change the past, right? Wrong. So very wrong. The results showed that your future decision about whether to measure affects how the particle behaved in the past. If you choose to measure, it went through one slit. If you choose not to measure, it went through both. This is Wheeler's delayed choice experiment, proposed by physicist John Wheeler and actually performed multiple times, and it keeps suggesting that somehow our future choices influence past events. Time apparently works differently at the quantum level, which is not the comforting news you want about the fundamental fabric of reality. Let's take a step back and think about what this means for matter itself. Every single atom in your body is made of these quantum particles that don't have definite properties until measured. Your electrons aren't in specific places, they're probability clouds. The quarks making up your protons and neutrons are doing the same quantum nonsense. At the most fundamental level, you're not made of solid stuff. You're made of probability waves that happen to collectively create the appearance of solid stuff when observed. You're essentially a standing wave pattern that's convinced itself it's a person, which is simultaneously profound and deeply weird. Every object you've ever touched, every solid surface, every physical thing in your experience, none of it is actually solid in the way you think it is. It's all quantum fuzziness that evolution trained your brain to interpret as solidity because everything is a probability cloud until observed wasn't useful information for avoiding predators. And it's not like this is some exotic behavior that only happens in carefully controlled laboratory conditions with exotic particles. This is literally everything, all the time. The only reason you don't see quantum effects in everyday life is because bigger objects involve so many particles that all their quantum weirdness averages out into apparently classical behavior. It's like how individual people can be unpredictable, but crowds follow statistical patterns, except in this case, individual people are quantum particles being absolutely bonkers, and crowds are everyday objects pretending to be normal. Your chair is behaving classically not because the quantum rules stop applying at larger scales, but because trillions of particles all doing quantum nonsense simultaneously happens to average out to something that looks stable. Underneath that stability is pure probability and uncertainty, a roiling quantum chaos that's just barely holding itself together long enough to let you sit down. Now here's another fun thought that'll keep you up at night. If particles don't have definite properties until measured, what does that mean for all the particles in the universe that nobody's measuring? Are they just floating around in superposition, being everywhere and nowhere, having all possible properties simultaneously? According to quantum mechanics, yes, basically. Unobserved particles exist in these fuzzy quantum states, and only observation forces them to commit to specific values. This leads to the famous Schrödinger's cat thought experiment, where a cat in a box with a quantum device is supposedly both alive and dead until you open the box and observe it. Schrödinger proposed this to show how ridiculous quantum mechanics seems when applied to everyday scales, but the joke's on him because the math actually works out that way. The cat really is in a superposition of alive and dead states until observation collapses the wave function, which is absolutely wild and probably why we don't run this experiment with actual cats anymore. It's disturbing enough as a thought. Experiment. The implications of all this for the nature of matter are staggering. Matter, in the sense of definite objects with definite properties existing in definite locations, doesn't exist at the quantum level. What exists are probability amplitudes, wave functions, superpositions of possibilities. Matter is what happens when you observe these quantum possibilities and force them to commit to something definite. Before observation, there's just this cloud of potential, this mathematical description of what might be where with various probabilities. After observation, suddenly there's a particle with a location and momentum and all the properties we associate with real physical objects. But which one is the real state? The fuzzy quantum superposition or the definite classical observation? Most physicists would say the quantum state is more fundamental, more real, and that classical reality is what emerges when quantum systems interact with measuring devices or environments in ways that destroy quantum coherence. The solid world you experience is an emergent property, something that appears when you coarse grain over the quantum details, like how a photograph looks like a continuous image from far away, but reveals itself to be discrete pixels when you zoom in. Except in this case, the pixels are probability clouds, and the photograph is everything you've ever seen or touched or thought was real. Let's talk about quantum entanglement while we're at it, because this is where quantum mechanics really commits to the bit of making no sense whatsoever. When two particles interact, they can become entangled, meaning their quantum states are linked even if they're separated by vast distances. Measure the spin of one entangled electron, and you instantly know the spin of its partner, even if that partner is on the other side of the galaxy. This isn't because one particle is sending a signal to the other, it's because they share a single quantum state that describes both particles together. They're not two separate things that happen to be correlated, They're genuinely a single quantum system split across space, which is the kind of non-local weirdness that made Einstein write grumpy letters about how this couldn't possibly be how reality works. Spoiler alert, it is how reality works, and Einstein was wrong about this one. Though to be fair, being wrong about quantum mechanics put him in excellent company with basically every physicist's intuition. The experimental verification of quantum entanglement came through something called Bell's theorem and subsequent test of Bell inequalities. Physicist John Bell proved mathematically that if quantum mechanics was correct, certain experimental results would violate what we'd expect from any classical hidden variable theory, any theory suggesting that particles have definite properties all along. We just don't know what they are until we measure. The experiments have been done countless times with increasingly tight controls, and quantum mechanics wins every time. There are no hidden variables. Particles genuinely don't have definite properties until measured. Entangled particles genuinely share non-local quantum states. Reality at the quantum level is just this strange, and no amount of wishing for classical behavior will make it otherwise. So what are we supposed to make of all this? The most honest answer is that nobody really knows. We've got the mathematics of quantum mechanics, which makes predictions with stunning accuracy, literally the most precisely tested theory in all of science. We can use quantum mechanics to build computers and lasers and MRI machines, to understand chemistry and materials science, to explain how the sun works. The theory works perfectly for making predictions. But what it means, what it's telling us about the nature of reality, that's where things get philosophical and contentious. There are multiple interpretations of quantum mechanics: Copenhagen, many worlds, pilot wave, objective collapse theories, and they all reproduce the same experimental predictions while telling radically different stories about what's actually happening. The Copenhagen interpretation says measurement causes wave function collapse, but doesn't really explain what counts as a measurement or why it happens. The many worlds interpretation says wave functions never collapse. Instead, the universe splits into multiple branches every time a quantum measurement could happen, which means there are countless parallel universes where every possible quantum outcome occurred. That's right. Somewhere in the multiverse there's a version of you who measured that electron in a different position, and another version who became a professional accordion player, and another version where dinosaurs never went extinct. The pilot wave theory adds hidden variables back in, suggesting particles always have definite positions guided by a quantum wave, but requires non-local faster-than-light influences. Every interpretation has weird implications that violate our common sense in different ways. There's no consensus on which one is correct, assuming any of them are, which is a delightful state of affairs for a field that's been around for nearly a century. But here's what we can say with confidence: matter doesn't exist in the way common sense suggests. Particles aren't little solid balls with definite properties. They're quantum entities that exist in superpositions until observed, that interfere with themselves, that remain connected across arbitrary distances through entanglement. The solid, definite, classical world we experience is something that emerges from quantum weirdness through a process we don't fully understand involving measurement and decoherence. At its most fundamental level, reality is fuzzy, probabilistic, and deeply strange. Your chair isn't really solid. It's a quantum probability distribution that's managing to look classical through sheer statistical weight. You aren't made of matter in the traditional sense. You're made of quantum fields experiencing localized excitations that somehow result in consciousness and the ability to contemplate just how weird your own fundamental nature actually is. This is the point where physics stopped being about describing the world we see and started being about accepting that the world we see is a comforting lie built on top of quantum strangeness. And somehow, impossibly, this gets even weirder when we start talking about what particles actually are at the deepest level. Because it turns out particles aren't even the fundamental building blocks. They're more like ripples in something even more bizarre and abstract. But we'll get to that particular nightmare in the next section, because reality wasn't done showing us how little we actually understand about the universe we're living in. So we've established that particles aren't really particles, and your senses are professional liars. Great start. Now let's talk about space and time, because apparently those aren't real either. And I don't mean that in some vague metaphorical sense. I mean that modern physics has some deeply disturbing evidence suggesting that the 3 dimensions of space and 1 dimension of time that you experience every day might be emergent properties. things that appear to exist but aren't actually fundamental to reality. It's like finding out that the operating system you've been using your whole life is just a graphical interface running on top of completely different code. Except in this case, the operating system is literally the fabric of space-time itself, and nobody's quite sure what the underlying code actually looks like. Let's start with the holographic principle, which is one of those ideas that sounds like pseudoscience until you realize it's supported by actual mathematical physics and comes from studying black holes. Here's the basic concept. All the information contained in a three-dimensional volume of space can actually be encoded on a two-dimensional surface surrounding that volume. Everything. Every particle, every field, every bit of data about what's happening in that 3D space can be represented on a 2D boundary, like a hologram that creates the illusion of depth when you look at it from the right angle. Which means, and I want you to really sit with this for a moment, the three-dimensional universe you're experiencing might actually be a projection from a two-dimensional information structure. You could be living in the cosmic equivalent of a hologram, experiencing depth that doesn't fundamentally exist. This isn't some random speculation someone came up with while high. This comes from serious work on black hole thermodynamics by physicists like Jacob Bekenstein and Stephen Hawking. They discovered that the amount of information a black hole can contain is proportional to the area of its event horizon, not its volume. Think about that. If you have a sphere, you'd expect the amount of stuff it can hold to depend on its volume, right? That's how storage works in 3 dimensions. But black holes apparently don't work that way. The information capacity scales with the surface area, like the black hole is fundamentally a 2-dimensional object that's just pretending to be 3-dimensional. This is similar to how your computer screen has a 2D array of pixels but can display 3D-looking images, except in this case, reality itself might be the image, and we're all pixels who don't realize we're flat. Gerard 't Hooft and Leonard Susskind took this black hole result and ran with it, proposing that this holographic property might not just apply to black holes, but to the universe as a whole. Their work suggested that our entire universe could be described by information encoded on a distant 2-dimensional boundary, with everything we experience as 3-dimensional space being a kind of projection or emergence from that 2D structure. It's like if you were a character in a video game who suddenly realized that everything in your 3D world is actually being rendered from 2D code and textures, and that your experience of depth and volume is just a very convincing illusion created by the game engine. Except you can't quit the game or see the code, you're stuck experiencing the projection as if it were fundamental reality. Now, the holographic principle gets even weirder when you combine it with string theory and something called ADS-CFT correspondence, which is this mathematical relationship discovered by Juan Maldacena that shows how a quantum field theory in a flat space can be exactly equivalent to a theory of gravity in a higher dimensional curved space. Basically, you can describe the same physics 2 completely different ways, one without gravity in fewer dimensions, one with gravity in more dimensions. And these descriptions are mathematically identical. It's like having 2 completely different languages that somehow convey identical information, which suggests that the number of dimensions might not be as fixed and fundamental as we thought. Maybe dimensions are just different ways of describing the same underlying reality, like how you can represent the same 3D object with 2D blueprints from different angles. Except in this case, we might be the 2D blueprints thinking we're the 3D object. The implications for space and time are pretty devastating if you think about it. Space might not be this fundamental stage where events happen. It might be an emergent property that appears from some deeper informational or quantum structure. Time might work the same way. Some approaches to quantum gravity, particularly theories developed by physicists like Carlo Rovelli and Lee Smolin, suggest that space-time is built from discrete quantum units, these tiny loops or networks of relationships that create the appearance of continuous space and flowing time when you zoom out. It's like how a digital photograph looks smooth and continuous until you zoom in far enough to see the individual pixels. Space-time might be pixelated at the Planck scale, about 10 to the negative 35 meters, which is so incredibly small that we'll probably never be able to probe it directly. But the math suggests it's there. Reality has a resolution limit, a fundamental graininess below which the concepts of distance and duration might not even make sense. And if space-time is emergent, what does that mean for everything happening in space-time? Well, it means your location isn't fundamentally real. Your movement through space might be an illusion created by changing relationships in some deeper quantum structure. The flow of time that feels so visceral and undeniable could be an emergent property that appears from timeless quantum entanglements and correlations. You think you're moving through space and time, but maybe you're just different configurations of some underlying quantum information network, and the sensation of motion and duration is how that network looks from the inside. It's like being a character in a flipbook animation who thinks they're smoothly moving through time, when really they're just a series of static images being flipped rapidly. Except the flipbook might not even exist. It might just be quantum correlations creating the appearance of sequential moments. The really unsettling part is that we don't have direct experimental evidence for any of this yet, because testing theories of quantum gravity is absurdly difficult. We'd need particle accelerators the size of galaxies, or the ability to probe energy scales that existed fractions of a second after the Big Bang. But the theoretical consistency is compelling, and the holographic principle keeps showing up in different areas of physics, which suggests it's pointing at something real about the structure of reality. Multiple independent lines of research, black hole physics, string theory, loop quantum gravity, tensor network models, all converge on this idea that space-time is not fundamental. That's not proof, but it's the kind of pattern that makes physicists pay attention, because the universe doesn't usually coincide like that unless there's something genuine underlying it. So you might be living in a hologram. Your three-dimensional experience of reality could be a projection from a two-dimensional information surface. Space and time might emerge from quantum entanglement and information theory, rather than being the fundamental arena where quantum stuff happens. The solid, continuous, three-dimensional plus-time universe that evolution trained you to perceive could be the ultimate optical illusion, a cosmic magic trick where depth and duration appear from something completely different underneath. Not exactly the comforting foundation for reality you were probably hoping for, but at least it explains why physics keeps getting weirder the deeper you look. You're literally trying to see through the illusion to the actual structure underneath, and that structure follows completely different rules than the emergent reality you experience. Now let's talk about something that should really bother you about our universe. 95% of it is missing. Not metaphorically missing, not we haven't found it yet missing. Fundamentally, completely, embarrassingly missing. We can see its effects, we can measure its gravitational influence, we can map where it should be, but we cannot detect the actual stuff directly, no matter how sophisticated our instruments get. This is dark matter and dark energy, and they make up the overwhelming majority of the universe while remaining completely invisible to us. Which raises an uncomfortable question. What if they're not actually real substances at all? What if they're glitches in our perceptual interface, artifacts of the fact that we're trying to understand a fundamentally different underlying reality using tools and concepts that don't actually apply? Let's start with dark matter, because this is where astronomers first realized something was terribly wrong. In the 1930s, Fritz Zwicky was studying galaxy clusters and noticed that galaxies were moving way too fast. Like they should have been flying apart based on the visible matter's gravity, but they weren't. They were held together by something invisible. Then, in the 1970s, Vera Rubin observed that stars in spiral galaxies rotate at roughly the same speed regardless of their distance from the center, which makes absolutely no sense if you only account for visible matter. The stars on the outer edges should be moving much slower, like how Neptune orbits the Sun more slowly than Earth does, but they don't. They're moving as if there's a massive halo of invisible matter surrounding the galaxy, providing extra gravity to speed up those outer stars. And this isn't just a couple weird galaxies, this is everywhere we look. Gravitational lensing observations, watching how massive objects bend light from background sources, show the same thing. There's way more mass than we can see. The cosmic microwave background radiation, the leftover light from the Big Bang, has specific patterns in its temperature fluctuations that only make sense if there's roughly 5 times more dark matter than regular matter in the universe. Galaxy formation simulations only work if you add dark matter to provide the gravitational scaffolding. Every independent line of evidence points to the same conclusion. Either there's a bunch of invisible matter out there that only interacts through gravity, or our understanding of gravity itself is wrong on cosmic scales. And here's the thing. Neither option is comforting. The standard explanation is that dark matter is some kind of particle that doesn't interact with electromagnetic radiation, which is why we can't see it directly. Maybe it's WIMPs, weakly interacting massive particles. Maybe it's axions, these hypothetical super-light particles that could be swarming around us right now. Maybe it's primordial black holes formed in the early universe. Scientists have been searching for decades, building increasingly sensitive detectors buried deep underground to shield them from cosmic rays, looking for even the tiniest hint of dark matter particles bumping into regular matter. The results? Nothing. Zero. Complete silence. Which is getting increasingly awkward, because we've essentially ruled out the most likely candidates, and we're running out of plausible hiding places for these particles. It's like knowing someone's in the room because their weight is making the floor creak, but you can't see them, hear them, smell them, or touch them no matter how hard you try. Now here's where the glitch hypothesis gets interesting. What if dark matter isn't a real substance at all, but an artifact of our model breaking down? Think about it like this. When you're playing a video game and you see weird visual glitches or objects floating in midair, that's not because there's some invisible matter in the game world. It's because the physics engine has limitations and approximations that break down in certain situations. What if gravity works differently on galactic scales than we think, and what we're interpreting as dark matter is actually just our equations failing to accurately describe reality at those scales? This is the idea behind MOND, modified Newtonian dynamics, which suggests that gravity behaves differently when accelerations are extremely small, like at the edges of galaxies. Change the gravity equation slightly in that regime, and suddenly you don't need dark matter to explain galaxy rotation curves. The problem with MOND and similar theories is they work great for some observations and terrible for others. They can explain galaxy rotation curves pretty well, but completely fail at explaining galaxy cluster dynamics, or the cosmic microwave background patterns. It's like finding a theory that perfectly explains why your car won't start but can't explain why the radio works. There's clearly something incomplete about it. Some physicists have proposed even more radical ideas, like emergent gravity theories where gravity isn't a fundamental force at all, but an entropic phenomenon that arises from quantum entanglement. In these theories, what we call dark matter could be a manifestation of how entanglement distributes through space in ways we don't understand yet. It's essentially suggesting that we're seeing the shadow of quantum information structure that we're misinterpreting as matter, because our classical gravity model doesn't account for quantum effects properly. Then there's dark energy, which is somehow even more baffling than dark matter. In the late 1990s, astronomers studying distant supernovae discovered that the universe's expansion is accelerating. Not slowing down like you'd expect from gravity pulling everything together, but speeding up like something is pushing space apart. They called this mysterious pushing force dark energy, which is a fancy name for we have absolutely no idea what's going on. It makes up about 68% of the universe's energy budget, and the leading explanation is that it's the energy of empty space, itself vacuum energy. Except when physicists try to calculate how much vacuum energy there should be based on quantum field theory, they get an answer that's wrong by about 120 orders of magnitude. That's not a typo. The theoretical prediction is 10 to the 120 times bigger than what we observe, which is literally the worst prediction in the history of physics. Congratulations, science, that's impressively wrong. What if dark energy, like dark matter, is an interface artifact? What if it's a sign that our model of cosmology breaks down on the larger scales? Some theories suggest that what we interpret as dark energy acceleration could actually be us living in an unusual region of a larger universe with different properties, or that we're misinterpreting how redshift works over cosmic distances. Others propose that it's a sign we're living in a higher dimensional space, and what we see as cosmic acceleration is really the effect of our 3D brain moving through a higher dimensional bulk. These ideas sound like science fiction, but they're serious proposals from reputable physicists trying to explain why 95% of the universe appears to be made of stuff we can't detect and don't understand. Here's the really unsettling interpretation that ties back to our earlier discussions. What if dark matter and dark energy are like error messages in our attempt to model reality? We're trying to describe the universe using general relativity and quantum field theory, these mathematical frameworks that assume space-time is fundamental and continuous. But we've already seen evidence that space-time might be emergent and discrete. We're trying to apply classical concepts to a fundamentally quantum and possibly holographic reality. It's like trying to run modern software on hardware from the 1980s. You're going to see glitches and errors because the framework isn't sophisticated enough to handle what's actually happening. Dark matter and dark energy might be those glitches, the places where our model breaks down because we're missing some crucial piece of the underlying structure. Consider the holographic principle again. If we're living in a projection from a 2D boundary, and that boundary encodes information using quantum principles we don't fully understand, then maybe what we perceive as dark matter and dark energy are actually features of the projection process itself. Maybe they're artifacts of how 3D space-time emerges from 2D quantum information, visible side effects of the translation between the fundamental description and our emergent experience. It's like how JPEG compression creates artifacts in images. Those artifacts aren't real features of the original scene, they're artifacts of the compression algorithm. If our 3D universe is a kind of decompression of 2D information, maybe dark matter and dark energy are the cosmic equivalent of compression artifacts, things that appear in the emergent description but don't correspond to anything fundamental in the underlying reality. Or here's an even wilder possibility. What if dark matter and dark energy are related to the limits of our observational horizon? We can only see a finite portion of the universe, about 46 billion light-years in any direction, which is our observable universe. Beyond that, space is expanding faster than light can travel, so we're causally disconnected from whatever's out there. What if what we interpret as dark matter and dark energy are actually the effects of information or matter or structure beyond our horizon, influencing our local patch through gravity, which can potentially extend beyond the observable universe? We'd see gravitational effects from things we can't observe directly, which would look exactly like invisible matter and energy affecting our local universe. From our perspective, trapped inside our limited observational bubble, we'd never be able to verify if that's what's happening because we can't see the source. The honest truth is, we don't know what dark matter and dark energy are. We don't know if they're real substances, modified gravity, quantum effects, holographic artifacts, influences from beyond our observable universe, or something else we haven't even imagined yet. We're essentially in the position of someone in the 1800s trying to explain quantum mechanics using only classical physics. We don't have the right conceptual framework yet, and our current theories keep giving us these massive gaps and anomalies that we're filling in with placeholder names like dark matter and dark energy. These names make it sound like we understand what we're talking about, but really they're just labels for our ignorance, polite ways of saying something weird is happening here and we have no idea what it actually is. What we can say is that 95% of the universe's content is completely invisible to us, interacts with regular matter in ways we don't understand, and might not even be real in the conventional sense. We're trying to build a complete picture of reality while missing 95% of the pieces, like trying to understand a movie when you can only see 5% of the frames. And the frames we can see are already weird enough. Quantum superpositions, emergent spacetime, holographic projections. Adding in the overwhelming majority of content that we can't see or directly detect should really make us question whether our model of reality is even close to accurate, or if we're fundamentally misunderstanding something so basic and essential. That everything we think we know is built on a flawed foundation. This is the universe we're living in, one where our senses evolve to lie to us, where particles refuse to exist properly, where space-time might be a holographic projection, and where 95% of everything is invisible and unexplained. We haven't even gotten to consciousness, time, or simulation arguments yet, and reality is already looking deeply suspicious. The cracks in reality's foundation aren't just visible at this point, they're massive chasms that our current physics theories are barely able to paper over with placeholder names and desperate speculation. And it's about to get even stranger because we haven't yet addressed the biggest mystery of all, the role of the observer in creating reality and what that means for the nature of consciousness itself. Alright, so we've established that your senses are unreliable, particles are probability clouds, space-time might be a holographic illusion, and 95% of the universe is missing in action. You'd think we'd hit rock bottom on the weirdness scale at this point, but oh no, the universe has been saving its best trick for now. Because it turns out that the act of observation, the simple fact that you're looking at something, fundamentally changes what that something is, and not in some subtle, negligible way, in a completely transform the nature of reality kind of way. Welcome to the measurement problem, where consciousness might not just be experiencing reality, but actively creating it moment by moment, which is either the most empowering thing you'll hear today or the most terrifying, depending on how you feel. About existential responsibility. Let's talk about what happens when you measure a quantum system, because this is where physics takes a hard left turn into philosophical nightmare territory. Remember how we discussed that particles exist in superposition until observed? Well, the process of going from superposition to definite state is called wave function collapse, and nobody, and I mean nobody, fully understands what's actually happening during that collapse. Before you measure an electron's position, it genuinely exists in a superposition of being in multiple places simultaneously. The wave function describes all these possibilities with their associated probabilities. Then you measure it, and suddenly, instantaneously, the wave function collapses and the electron has a definite position. All those other possibilities just vanish, poof, gone, like they never existed. Which raises some pretty uncomfortable questions. What counts as a measurement? What causes the collapse? And most disturbingly, is consciousness somehow involved in making reality definite? The standard Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg back when quantum mechanics was young and everyone was still optimistic about understanding it, basically punts on these questions. It says the wave function collapses when a measurement occurs, but it's frustratingly vague about what constitutes a measurement. Is it when a particle hits a detector? When the detector's reading is recorded? When a conscious observer looks at the recording? The Copenhagen interpretation kind of shrugs and says, measurements happen when systems interact with macroscopic measuring devices, which is not exactly a satisfying answer because it just pushes the question back. What makes something macroscopic? Enough to count as a measuring device? It's like defining a word using the same word, which would get you marked down on any vocabulary test but apparently passes for foundational physics. Here's where it gets really wild though. In the 1930s, mathematician John von Neumann analysed the measurement process mathematically and came to an unsettling conclusion. If you follow the quantum mechanics equations consistently, the collapse of the wave function can't happen at the level of physical instruments. Physical instruments are made of particles, which means they obey quantum mechanics too, which means they should also exist in superposition until observed. So if the detector is in superposition and the particle is in superposition, when does anything become definite? Von Neumann's analysis suggested that the collapse might occur only when a conscious observer becomes aware of the measurement result. Consciousness, actual subjective awareness, might be what makes quantum possibilities collapse into classical reality, which is absolutely bananas and also kind of awesome in a deeply unsettling way. This became known as the von Neumann-Wigner interpretation, after physicist Eugene Wigner picked up the idea and ran with it. Wigner argued that consciousness is fundamentally different from physical processes, and that only a conscious observation can collapse the wave function. He even proposed a thought experiment involving a friend in a closed lab performing a quantum measurement. From outside, Wigner would describe his friend and the quantum system as both being in superposition until he opened the lab and asked his friend what they observed. His friend, being inside, would say the wave function collapsed when they looked at the measurement device. Both descriptions are valid according to quantum mechanics, but they contradict each other. One says everything is in superposition, one says it collapsed. The only way to resolve this, Wigner suggested, is if consciousness plays a special role in collapsing wave functions. Your awareness, your subjective experience, might literally be what transforms quantum possibilities into definite reality. Now, before you get too excited about being a reality-creating god, most modern physicists don't actually buy the consciousness causes collapse interpretation, mostly because it seems to give consciousness this special privileged role that doesn't fit well with our understanding of brain function as physical processes. But here's the thing, nobody has a better explanation that doesn't also sound completely insane. The many worlds interpretation says consciousness doesn't collapse anything. Instead, the universe splits into multiple branches every time a measurement could happen, and your consciousness just follows one branch while other versions of you experience all the other outcomes in parallel universes. That's not exactly more reasonable, it just trades one flavor of crazy for another. Objective collapse theories propose that wave functions collapse spontaneously due to some unknown physical process when systems get large enough, but these theories require adding new physics beyond standard quantum mechanics, and we have no experimental evidence for them yet. The delayed choice experiment takes this observer problem and cranks it up to genuinely disturbing levels. Physicist John Wheeler proposed this in the 1970s as a thought experiment, and it's since been performed in real laboratories with actual photons, confirming the bizarre predictions. Here's the setup. You send a photon through a double-slit apparatus, but you don't decide whether to measure which slit it goes through until after it's already passed the slits. If you choose to measure which path, the photon goes through one slit like a particle and creates two bands on the screen. If you choose not to measure, it goes through both slits like a wave and creates an interference pattern. The key point is you're making this choice after the photon has already gone through the slits. Your future decision is somehow affecting the photon's past behavior, determining whether it went through one slit or both retroactively. Think about what this means for a second. The photon doesn't have a definite history until you decide how to observe it. It exists in a superposition of histories, went through left slit, went through right slit, went through both, and your measurement choice selects which history becomes real. It's like if you took a photograph, but the photograph didn't show anything definite until you decided whether to look at it, and your decision somehow determined what was in the photograph all along, even though the photo was taken in the past. Time apparently doesn't work the way we think it does at the quantum level. The future can influence the past, or more accurately, the past doesn't fully exist as a definite sequence of events until observed, which really should bother you a lot more than it probably does because you're getting numb to quantum weirdness at this point. Wheeler took this idea even further with his delayed choice quantum eraser experiment, which has been performed multiple times and keeps confirming the disturbing predictions. In this version, you can make a measurement that reveals which path the photon took, but then you can erase that information afterward. And here's the kicker. If you erase the which path information, the interference pattern reappears, even though the photon already hit the detector. Your choice to erase or keep the which path information retroactively determines whether the photon behaved as a wave or particle in the past. It's like being able to edit history, except you're not changing what happened, you're determining what happened in the first place. The past is apparently negotiable, pending your observational choices in the future, which is the kind of time-bending nonsense that science fiction writers would reject as too implausible. Now let's connect this back to consciousness. These experiments show that observation fundamentally changes quantum systems. But what is observation really? Is it just any interaction with a measuring device? If you set up a detector but never look at the results, does the wave function collapse? Some interpretations say yes, the interaction with the detector is enough. Others say no, the information has to be observed by a conscious entity for collapse to occur. There's no consensus, and the experiments can't definitively tell us because we can't easily test what happens when a quantum measurement occurs, but no conscious being ever learns the results. We're stuck in this weird limbo where consciousness might be essential to reality, or might be completely irrelevant, and our current physics theories can't settle the question. Here's another angle on this that's even more unsettling. If wave function collapse requires consciousness, and consciousness is a product of brain activity, and brain activity is made of particles that obey quantum mechanics, then we have a circular problem. Consciousness requires definite classical brain states, but definite classical states require consciousness to collapse quantum superpositions. It's like the chicken and egg problem, except both the chicken and egg are in quantum superposition until observed, and the observation requires a conscious chicken observing a definite egg, and we're right back where we started. Some physicists have proposed that consciousness might be quantum mechanical itself, that your subjective experience arises from quantum processes in your brain, like microtubules in neurons maintaining coherent quantum states. This is the Orca theory proposed by Roger Penrose and Stuart Hameroff, which suggests consciousness involves quantum gravity effects in the brain. Most neuroscientists are deeply skeptical of quantum consciousness theories, arguing that the brain is too warm and noisy for delicate quantum coherence to survive. Decoherence, the process where quantum superpositions collapse due to interactions with the environment, happens incredibly fast in warm, wet environments like biological tissue. We're talking timescales of femtoseconds to picoseconds, way too fast for quantum effects to play any meaningful role in brain function. But Penrose and Hameroff argue that biological systems might have evolved ways to protect quantum coherence, using specially structured proteins to shield quantum processes from environmental decoherence. It's possible, though unproven, and most of the neuroscience community thinks consciousness can be explained perfectly well through classical neural network dynamics without invoking quantum mechanics. Though to be fair, we don't actually understand consciousness at all, so ruling out quantum effects might be premature. Regardless of whether consciousness itself is quantum, the measurement problem remains. Something transforms quantum superpositions into definite classical outcomes. That something could be consciousness, or it could be decoherence from environmental interactions, or it could be spontaneous collapse processes we haven't discovered yet, or it could be that nothing collapses and the universe just keeps splitting into parallel branches forever. Every interpretation has weird implications. The consciousness interpretation makes you the creator of reality, but requires explaining how unconscious measuring devices work. The many worlds interpretation avoids collapse entirely, but commits you to an exponentially expanding multiverse of parallel realities. Objective collapse theories add new physics we've never observed. Take your pick of which flavor of crazy you prefer. They're all on the menu and none of them are particularly digestible. Here's what really gets me about all this. We use quantum mechanics every single day. Your smartphone, your computer, LED lights, MRI machines, GPS satellites, all of these technologies depend on quantum mechanics working exactly as the math predicts. Quantum mechanics is literally the most precisely tested theory in the history of science. We can predict experimental outcomes to 10 or 15 decimal places. The technology works flawlessly. And yet we have absolutely no consensus on what the theory actually means, on what's happening at a fundamental level when we make measurements, on what role, if any, consciousness plays in the process. It's like having a car that runs perfectly but having 5 completely different and mutually contradictory explanations for how the engine works, and all 5 explanations make identical predictions about what happens when you press the gas pedal, so you can't figure out which one is right. The implications for the nature of reality are pretty staggering, though. If consciousness does play a role in wave function collapse, then reality before conscious observation is fundamentally different from reality after. The universe before the evolution of consciousness would have been this vast cloud of quantum superpositions with no definite properties. Particles wouldn't have definite positions or momenta. Even the cosmic microwave background radiation, the light from the Big Bang, might not have had definite properties until conscious observers evolved and measured it, at which point those observations retroactively selected which quantum history became real. The entire history of the universe might be in some sense created or at least made definite by conscious observation, which is either profound or absurd or both. Some physicists take this even further and propose that consciousness isn't just collapsing wave functions, but is actually fundamental to the universe, more basic than matter or energy. This connects to ideas we'll discuss later about panpsychism, but the basic notion is that trying to explain consciousness as emerging from unconscious matter might be backwards. Maybe consciousness is the fundamental thing, and matter is what consciousness looks like from the outside when we try to describe it mathematically. The universe might be made of consciousness having experiences, with physics being the mathematical structure describing how those experiences relate to each other. Which sounds completely insane until you remember that we have no idea how unconscious matter could possibly give rise to subjective experience in the first place, so maybe the insane idea is worth considering. What we can say with confidence is that observation matters in quantum mechanics. Not just in some trivial sense that you need to look at things to know about them, in a fundamental sense where the act of observation literally transforms what the thing is. Particles don't have definite properties independent of observation. They exist in superpositions that become definite only when measured. Whether consciousness is required for this process, or whether interaction with any macroscopic system is sufficient, remains hotly debated. But either way, the quantum world teaches us that reality isn't sitting out there fully formed waiting to be discovered. Reality is something that unfolds, that becomes definite through the process of observation and measurement, whether that observation requires consciousness or not. The naive view that there's an objective external world existing completely independent of observers, with definite properties that we simply discover through measurement, that view is dead. Quantum mechanics killed it, performed an autopsy, and the results are clear. Reality at its most fundamental level involves relationships between observers and observed systems, not objects existing in isolation. You can't separate the observer from the observed, can't cleanly divide the universe into stuff that exists and stuff that's measuring what exists, because the act of measurement is part of what creates definite existence in the first place. We're not passive observers looking at a pre-existing reality. We're active participants in a process that creates definite reality through observation, whatever observation turns out to actually be. This is one of those places where physics has completely outpaced philosophy. Philosophers spent centuries debating whether reality is objective or subjective, whether consciousness is fundamental or emergent, whether we create reality or discover it. And then quantum mechanics came along and said yes to multiple contradictory options simultaneously, because apparently the universe's answer to deep philosophical questions is, it's more complicated than you thought, and also weirder. The measurement problem isn't solved, consciousness's role isn't understood, and we're stuck with a theory that makes perfect predictions but offers no clear picture of what's actually happening beneath those predictions. It works brilliantly as a mathematical tool and fails completely as a philosophical explanation, which is somehow fitting for a universe that seems designed to confuse anyone trying to understand it. So where does this leave us? With the uncomfortable knowledge that observation changes reality, that consciousness might or might not play a special role in that process, that the past might not be fully determined until observed, and that the most fundamental level of reality involves weird quantum relationships between observers and observed systems that we don't fully understand. Not exactly the solid foundation for reality you were probably hoping for when you started this video, but hey, at least it's consistently weird, and that's something. The universe is lying to us through our senses, hiding 95% of its contents, possibly being a holographic projection, and now potentially requiring consciousness to make itself definite. The deception runs deep, folks, and we're barely scratching the surface of how strange things really are. So we've established that reality is a quantum probability nightmare, where consciousness might be creating definite states through observation. Now let's add another layer of existential weirdness to the pile. What if the universe isn't just behaving strangely, but is literally running on code? What if reality at its most fundamental level is computational, a massive information processing system executing algorithms that create everything from galaxies to your morning coffee? Welcome to digital physics, where the universe might actually be a computer, and we're all just extremely elaborate subroutines running on cosmic hardware that we're only beginning to understand. Here's the thing that should immediately make you suspicious about the fundamental nature of reality. Physics has limits. Not practical limits like, we don't have big enough telescopes, but hard theoretical limits baked into the structure of space-time itself. There's something called the Planck length, which is about 10 to the negative 35 meters, so absurdly tiny that if you scaled an atom up to the size of the observable universe, the Planck length would still be smaller than a human hair. Below this scale, the concepts of distance and space stop making sense because quantum fluctuations in space-time become so violent that you can't meaningfully talk about geometry anymore. And there's the Planck time, about 10 to the negative 44 seconds, which is the smallest meaningful unit of time. Below this, causality itself gets fuzzy. These aren't just measurement limitations, they appear to be fundamental features of reality, like the universe has a minimum resolution below which nothing exists. Sound familiar? That's right, pixels. Reality has pixels. Think about what this means. If space has a minimum possible division, and time has a minimum possible interval, then space-time isn't actually continuous like we experience it. It's discrete, quantized, broken into fundamental units like frames in a video or pixels on a screen. You're not smoothly moving through continuous space. You're jumping between discrete spatial positions at discrete time intervals, so fast that your brain interprets it as smooth, continuous motion. It's like how a movie is really just 24 still frames per second, but looks like smooth motion to your eyes, except in this case it's 10 to the 44 frames per second, and the projector is reality itself. The universe might literally be rendering existence frame by frame, position by position, with Planck scale units serving as the fundamental grid on which everything runs. Now, if reality has discrete units like a computer, the obvious question is, what's the program? Enter Stephen Wolfram, a physicist and mathematician who got really obsessed with this question, and wrote a 1,000-page book called A New Kind of Science that basically argues the universe is a giant cellular automaton running simple. Computational rules? Wolfram studied these things called cellular automata, grids of cells that follow extremely simple rules like turn on if your neighbor is on, turn off if two neighbors are on, and discovered something wild. These ridiculously simple rules, when run for enough iterations, can produce staggeringly complex patterns that look completely random and unpredictable. even though they're generated by deterministic rules. Some of them create structures that look eerily similar to natural patterns: shells, plants, turbulence, even particle physics phenomena. His most famous example is Rule 30, a cellular automaton with such a simple rule you can explain it in one sentence, but when you run it, it generates complexity that appears completely random. It's so effectively random that Wolfram used it as a random number generator in Mathematica software for years. Here's the kicker. The pattern it produces is computationally irreducible, meaning there's no shortcut to predict what the pattern will look like a million steps in the future, except to actually run all million steps. You can't compress the computation, you have to let it play out. This matters because it means you could have a universe running on incredibly simple rules at the fundamental level, but those rules would generate complexity so intricate and apparently random that observers inside the system would have no way to predict outcomes except by watching them unfold. Sound like our universe, where we can't predict quantum outcomes, where weather becomes chaotic, where three-body gravitational problems have no general solution? Yeah, computational irreducibility could explain all of that. Wolfram goes further and proposes that the laws of physics themselves might emerge from simple computational rules operating on a discrete space-time network. In this view, particles aren't fundamental objects. They're persistent patterns in the computational substrate, like gliders in Conway's Game of Life that move across the grid, even though they're really just patterns of cells turning on and off. Space, time, matter, energy, all emergent properties of underlying computation. The universe isn't being governed by laws of physics written down somewhere in cosmic code. The universe is the computation, and what we call laws of physics are just descriptions of the patterns we notice in how that computation unfolds. It's like how the rules of chess create complex strategic patterns, but those patterns aren't separate from the rules. They're what the rules look like when you play many games. Now let's talk about information theory's role in all this, because there's a growing movement among physicists suggesting that information, not matter or energy, is the most fundamental thing in the universe. John Wheeler, the physicist who gave us black holes and wormholes, coined the phrase "it from bit," the idea that every physical thing, every it, derives its existence from yes or no answers to questions, from bits of information. In this view, reality is fundamentally informational, and matter is just a way of storing and processing that information. Your body isn't made of atoms that happen to contain information. Your body is information configured in a particular pattern, happening to look like atoms when observed at the right scale. The difference is subtle but profound. It's the gap between things that have information and information that has things. This connects beautifully with quantum mechanics, because quantum mechanics is fundamentally about information. A quantum state is described by a wave function, which is essentially a probability distribution, information about possible outcomes. Quantum entanglement links the information states of particles across arbitrary distances. Measurement extracts information from quantum systems and makes it classical. The whole theory is naturally expressed in informational terms, with concepts like entropy, information capacity, and quantum bits being central to how we understand quantum behavior. Some physicists, like Seth Lloyd at MIT, have calculated that the universe has processed about 10 to the 120-bit operations since the Big Bang, treating cosmic evolution as one enormous quantum computation. The universe is computing itself into existence, processing information about what should happen next based on its current state and the rules it's running. Quantum computers make this even more explicit. In a quantum computer, information is stored in quantum bits or qubits that can exist in superposition, allowing parallel processing of multiple computational paths simultaneously. When you measure the qubits, you collapse their superposition and extract classical information from quantum computation. The process of quantum computing, preparing states, letting them evolve according to quantum rules, measuring outcomes, is literally identical to how the universe operates according to quantum mechanics. The universe has been quantum computing all along. We're just now building machines that deliberately harness this computational structure. Every particle interaction, every quantum measurement, every evolution of quantum fields is information processing happening at the Planck scale, with reality as the output. Here's where this gets philosophically weird. If the universe is computational, running algorithms on discrete spacetime, then what's the difference between real physics and a simulation? If two computational systems follow identical rules and produce identical outputs, are they fundamentally different? This is the computational equivalence principle. Sufficiently complex computations are equivalent regardless of the substrate they run on. A cellular automaton that perfectly mimics quantum field theory isn't just similar to quantum field theory, it is quantum field theory from an informational perspective. The physical implementation stops mattering once you reach computational equivalence. Which means if someone built a computer powerful enough to simulate our universe's physics perfectly, the simulated universe would be just as real as ours from the perspective of beings inside it. There'd be no experiment they could perform to prove they're in a simulation rather than base reality, because the simulation would be computationally indistinguishable from the real thing. This is deeply unsettling, but also kind of inevitable once you accept the universe is computational. If reality is algorithms running on space-time hardware, then those same algorithms could run on different hardware and produce identical results. The universe could be running on quantum fields and Planck-scale geometry, or it could be running on some other computational substrate entirely, and as long as the algorithms match, the resulting reality would be identical. You can't prove you're not in a simulation without knowing what the simulation is being run on, and if you're inside the system, you can never access the hardware layer to check. It's turtles all the way down, or rather it's algorithms all the way down, and at some point you just have to accept that the algorithms are the reality, rather than a description of something more fundamental beneath them. The thermodynamic argument for computational universe is fascinating too. There's this thing called Landauer's principle, which says that erasing information requires a minimum amount of energy. Roughly speaking, information is physical and has a real energy cost. This connects computation directly to thermodynamics. Black holes are the ultimate information storage devices, with their entropy proportional to surface area as we discussed earlier. Hawking radiation from black holes involves information processing, with debates about whether information is preserved or lost when matter falls into black holes. The whole universe has an information budget determined by its size and energy content, and cosmology becomes an exercise in tracking how that information is distributed and processed over time. The arrow of time itself, the fact that entropy increases and the past is different from the future, might be fundamentally about information flow, about the universe computing its way forward through state space, generating new information as it goes. Now, some physicists take this computational view to wild extremes. Max Tegmark has this mathematical universe hypothesis suggesting that all mathematically consistent structures exist, and our universe is just one mathematical object among infinite possibilities. The reason math describes physics so well isn't because we discovered some abstract truths, it's because physical reality literally is mathematics, and we're mathematical patterns that happen to be conscious. The universe doesn't just run on mathematics, it is mathematics, with physics being what mathematics looks like from the inside when you're a pattern complex enough to observe itself. This is either the most elegant unification of mathematics and physics imaginable, or it's taking the computational metaphor way too seriously, depending on your tolerance for ontological speculation. Edward Fredkin proposed something called digital philosophy, arguing that the universe is literally a cellular automaton running on discrete space-time, with all physics emerging from simple local rules at each point. His work inspired a lot of research into discrete physics and cellular automaton universes. The challenge is finding the right rule set. You need rules simple enough to be fundamental but complex enough in their consequences to reproduce all observed physics. Nobody's found that rule set yet, though various candidates have been proposed. Wolfram thinks his hypergraph approach might be it, where spacetime is a network of nodes and edges that evolves according to simple replacement rules, with space and time emerging from the structure and evolution of this network. It's early days, and the theory needs a lot more development before it can make testable predictions, but the basic idea that simple computational rules at the Planck scale could generate all observed physics is genuinely compelling. One of the striking things about the computational view is how naturally it explains why the universe has laws at all. If reality is just stuff existing, why should it follow consistent rules? But if reality is computation, then of course it follows rules. The rules are the algorithm being executed. The universe can't not follow its computational rules any more than a chess game can violate the rules of chess while still being chess. The fact that we can do science, can discover regularities, can make predictions based on mathematical laws, stops being this mysterious cosmic coincidence and becomes a trivial consequence of reality being algorithmic. The miracle isn't that the universe obeys laws. The miracle is that we're complex enough patterns in the computation to notice those laws and understand them mathematically. This also potentially explains why mathematics is unreasonably effective at describing physics, as physicist Eugene Wigner famously puzzled over. If the universe is computational, then of course mathematics describes it perfectly. Mathematics is literally the language of computation. We're not discovering some mysterious pre-existing harmony between abstract math and concrete reality. We're discovering that reality is mathematical structure, computational processes unfolding according to formal rules, and when we do mathematics, we're literally studying the native language of existence itself. Math works because reality is math, just from a different perspective. Like how studying the source code of a video game tells you exactly how the game behaves, not because there's some mysterious correspondence between code and behavior, but because the code is the behavior when executed. Here's the practical implication of all this. If the universe is computational and space-time is discrete, then there are ultimate limits to how much information and computation can occur in any finite region. The Bekenstein bound says the maximum entropy in a spherical region is proportional to the surface area of the sphere. The Margolis-Levitin theorem says there's a maximum rate at which a physical system can evolve from one state to another, determined by its energy. These aren't just practical limitations, they're fundamental constraints on information processing in our universe. You can't build an infinitely powerful computer, even in principle, because physics caps how much computation is possible. The universe itself is the most powerful computer that can exist within the laws of physics, using all available matter and energy to compute its own evolution. We're living inside the ultimate supercomputer, running the ultimate program, and all our computers are just tiny subroutines borrowing computational capacity from cosmic resources. The computational universe hypothesis has one more wild implication. If reality is algorithmic, then consciousness might be too. Your subjective experience, your sense of self, your thoughts and feelings, all of it could be computational processes running on the biological hardware of your brain, which is itself running on the computational substrate of quantum fields and space-time. You're not a physical object that happens to compute. You're a computation that happens to look like a physical object when viewed at the right scale. The hard problem of consciousness, trying to explain how physical brain activity produces subjective experience, might be a category error. Maybe experience doesn't emerge from computation. Maybe experience is what certain kinds of computation feel like from the inside. When the universe computes a sufficiently complex self-referential pattern that models itself and its environment, that pattern experiences itself as consciousness. You're not watching the computation. You are the computation, experiencing your own execution in real time. So where does this leave us? With the possibility that reality is fundamentally computational, running simple algorithms at the Planck scale that generate all the complexity we observe through computational irreducibility. Space and time are discrete, quantized into fundamental units like pixels and frames. Information is more fundamental than matter or energy, with physical objects being patterns of information configured in particular ways. The laws of physics aren't external rules imposed on reality. They are reality, the algorithms being executed, with everything we observe being the output of cosmic computation. Mathematics describes physics perfectly because physics is mathematics, computational processes that we're studying from the inside while being made of the very processes we're studying. The universe is a computer computing itself into existence, and we're subroutines complex enough to wonder about our own computational nature, which is either deeply profound or hilariously recursive or both. And naturally, this raises yet another disturbing question. If reality can be computational, and computation can be simulated, then how would we know we're not living in a simulation? But that's a nightmare for the next section. So we've established that the universe might be a giant computer running algorithms at the Planck scale. Now let's address the elephant in the room, or rather, the conspicuous absence of elephants, aliens, or any other intelligent life forms anywhere in the observable universe. Because here's something that should really bother you. We're completely alone. Or at least we appear to be completely alone, which is weird considering there are roughly 200 billion trillion stars in the observable universe, many with planets, many of those planets in habitable zones where liquid water could exist. The sheer mathematical probability suggests intelligent life should be everywhere, but when we look up at the sky with increasingly sophisticated instruments, we see exactly nothing. No alien signals, no megastructures, no signs of technological civilizations reshaping their solar systems, just silence, deafening, cosmic silence. This is the Fermi paradox, and it has some deeply disturbing possible explanations, one of which is that we might be living in a simulation specifically designed to keep us isolated. The paradox is named after physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950, "Where is everybody?" He was pointing out the contradiction between high probability estimates for alien civilizations and the complete lack of evidence for them. Let's break down why this is so weird. The Milky Way galaxy is about 13 billion years old. Earth is only 4.5 billion years old. There's been plenty of time for civilizations to arise on older planets, develop technology, and spread across the galaxy. Even with slower-than-light travel, a civilization could colonize the entire galaxy in just a few million years using self-replicating probes, a blink of an eye on cosmic timescales. So why isn't the galaxy teeming with alien civilizations and their artifacts? Why haven't they colonized Earth already, or at least sent a postcard? The silence is so complete and so statistically improbable that it demands explanation. There are numerous proposed solutions to the Fermi paradox, and they range from optimistic to apocalyptic. Maybe intelligent life is incredibly rare. Maybe the jump from single-celled organisms to complex multicellular life is a bottleneck so narrow that Earth is a fluke. Maybe life is common, but intelligence is rare. Maybe intelligence is common, but technological civilizations destroy themselves shortly after developing advanced technology, like we're currently doing such a great job of with climate change and nuclear weapons. That's called the Great Filter, and the terrifying question is whether the filter is behind us, meaning we're incredibly lucky to have made it this far, or ahead of us, meaning there's some inevitable catastrophe that wipes out technological civilizations before they can spread to the stars. Not exactly comforting bedtime thoughts. Or maybe aliens exist but they're not interested in contacting us. Maybe we're in a cosmic zoo or nature preserve where advanced civilizations have agreed to leave primitive species like us alone to develop naturally, which is both patronizing and slightly reassuring. Maybe interstellar travel is harder than we think, or maybe civilizations develop inward rather than outward, building virtual realities and exploring inner space rather than bothering with the messy business of colonizing actual planets. Maybe the universe is full of civilizations all quietly minding their own business, and we're the weird ones expecting everyone to be broadcasting their presence and building galactic empires. These explanations are possible, but they require a lot of assumptions about alien psychology and motivation, which we have exactly zero data on. Here's where the simulation hypothesis enters as a genuinely creepy explanation for the Fermi paradox. What if we don't see aliens because this simulation wasn't designed to include them? Think about it. If you're running an ancestor simulation, a detailed recreation of past civilizations to study history or for entertainment, you don't need to simulate the entire universe. You just need to simulate the local environment convincingly enough that the simulated beings can't tell they're in a simulation. Maybe Earth and our solar system are rendered in high detail, while the rest of the universe is just a skybox, a backdrop with no actual content. Like how video games only fully render the area around the player character and use lower detail models for distant objects to save processing power. If we're in a simulation, there'd be no point wasting computational resources simulating billions of alien civilizations that we can't interact with anyway. Just make the sky look right, sprinkle in some distant galaxies for authenticity, and call it good enough. This would explain the Fermi paradox perfectly. We don't see aliens because they're not part of the simulation. The universe appears huge and full of potential for life because that makes the simulation more believable, but actually populating it with billions of civilizations would be computationally expensive and unnecessary. It's like the Truman Show on a cosmic scale. Everything you can directly observe is real and detailed, but the background is just convincing scenery. The simulation only needs to fool the subjects inside it, and from our perspective inside the system, we can't tell the difference between an actually populated universe and a mostly empty universe with convincing window dressing. This is either a brilliant solution to the Fermi paradox or peak paranoid solipsism, possibly both. Now let's talk about Nick Bostrom's simulation argument, which is one of those philosophical papers that makes you want to lie down and stare at the ceiling for a while. Bostrom, a philosopher at Oxford, published this argument in 2003, and it's elegant, disturbing, and logically airtight in a way that's really annoying if you were hoping to dismiss simulation theory as science fiction nonsense. Here's the basic structure. Bostrom proposes that at least one of three statements must be true. 1. Almost all civilizations at our current level of development go extinct before reaching technological maturity, before they develop the capability to run detailed ancestor simulations. 2. Civilizations that survive to technological maturity almost never have any interest in running ancestor simulations of their evolutionary history. 3. We're almost certainly living in a simulation right now. Those are your options. Pick your poison. Let's break down why this argument works. Assume that some civilizations survive long enough to develop incredibly powerful computers capable of running detailed simulations of conscious beings. We're talking post-human civilizations with computational resources we can barely imagine. Quantum computers, molecular computing, whatever comes next. If even a tiny fraction of these civilizations choose to run ancestor simulations to study history, for entertainment, or for research, they'd run thousands or millions of simulations each. Every simulation would contain billions of conscious beings experiencing what they think is base reality. So do the math. If there are, say, 100 base reality civilizations, each running 1,000 simulations, you've got 100 base realities and 100,000 simulations. If you're a random conscious observer, you're statistically way more likely to be in one of the simulations than in base reality. The numbers just overwhelm you. Unless almost no civilizations survive or almost none of them run simulations, you're probably simulated. Welcome to the probability nightmare. The first horn of the trilemma, civilizations go extinct, is depressing but plausible. Maybe there really is a great filter ahead of us, some universal trap that technological civilizations fall into. Nuclear war, engineered pandemics, runaway artificial intelligence, environmental collapse, pick your apocalypse. If nearly every civilization destroys itself before developing simulation technology, then there are no post-human civilizations running simulations, so we're probably not in one. But this means we're doomed, probably sooner rather than later, which is not exactly a cheerful conclusion. It's like finding out you're not in a simulation, but only because everyone dies before getting simulation technology. Not sure that's actually better, honestly. The second horn, civilizations lose interest, requires assuming that no matter how diverse and creative future civilizations become, essentially none of them want to study their past by running simulations. Maybe they find it unethical to create conscious beings in simulations who don't know they're simulated. Maybe they're too busy with other pursuits to care about ancestor simulations. Maybe simulated beings have rights and creating them becomes heavily regulated or banned. This is possible, but it only takes a tiny fraction of civilizations running simulations to make the numbers favor us being simulated. So you'd need an incredibly strong universal taboo or technological limitation preventing essentially all mature civilizations from running ancestor simulations. That seems like a big assumption given how diverse motivations and ethics might be across different species and cultures. Which leaves the third horn. We're in a simulation. This one is wild because it doesn't require civilizations to go extinct or to have uniform preferences. It just requires that some civilizations sometimes run ancestor simulations, which seems like a pretty mild assumption. And once you accept that premise, the statistical argument becomes really hard to escape. If you're a conscious observer and you know that simulated conscious observers vastly outnumber base reality conscious observers, you should rationally assign high probability to being in the majority group. It's like if there's one original painting and 10,000 perfect copies, and you're looking at one of them in a museum, you should assume you're probably looking at a copy unless you have specific evidence otherwise. We don't have specific evidence we're in base reality, so Bostrom's argument suggests we should seriously consider the possibility that we're simulated. Now, the natural question is, how would we test this? Are there experiments we could run or observations we could make that would reveal we're in a simulation? This is where things get tricky and hilarious, because most proposed tests rely on finding glitches or computational limitations in the simulation. Some physicists have suggested looking for signs that the universe is running on a discrete lattice, that spacetime is pixelated at the Planck scale. We've already discussed how Planck limits might indicate discrete spacetime, but that's also what you'd expect from quantum gravity whether or not you're in a simulation, so it's not really evidence either way. Other proposals involve looking for errors in the simulation, places where the computational shortcuts become visible. Like looking for repeated patterns in supposedly random cosmic phenomena, or statistical anomalies that suggest procedural generation rather than truly random processes. The problem is that a sufficiently advanced simulation could avoid detectable glitches. If the simulators have computational resources vastly beyond our understanding, they could make the simulation smooth enough that we'd never find errors. It's like how modern video games have gotten so good at rendering realistic environments that you'd need to look very carefully to spot the tricks they're using. A civilization with millions of years of technological development beyond us could probably simulate our universe perfectly without leaving any evidence we could detect. And even if we did find evidence, how would we know it's a glitch rather than just new physics we don't understand yet? Every time we discover something weird about the universe, quantum entanglement, dark energy, whatever, we could say, aha, simulation glitch, but we could equally say, aha, interesting new physics. There's no way to tell the difference from inside. The system. Here's another disturbing angle. If we're in a simulation, the simulators might be monitoring for simulation awareness. If the simulation is running for research or historical accuracy, having the subjects become aware they're simulated might corrupt the data. So maybe there's a rule. Any simulation that becomes aware of its simulated nature gets shut down or reset. This creates a kind of anthropic selection effect where we can't observe evidence of simulation because universes where inhabitants discover they're simulated don't last long enough to publish papers about it. The only stable simulations are ones where the inhabitants never figure it out, which means we're either not simulated or we're simulated but will never be able to prove it, because the simulation will end before proof becomes widely accepted. This is the kind of unfalsifiable paranoia that makes philosophers giggle and scientists grind their teeth in frustration. The simulation hypothesis also provides a neat answer to fine-tuning problems in cosmology. The universe's physical constants appear to be precisely calibrated to allow complex chemistry and life, change the strength of gravity or the electromagnetic force by tiny amounts, and you get universes with no stars, no atoms, no possibility of complexity. This seems suspicious, like the universe was designed for us. The multiverse hypothesis explains this by saying infinite universes exist with all possible physical constants, and we're obviously in one that can support life because we wouldn't be here to observe otherwise. But the simulation hypothesis offers an alternative. Maybe the physical constants were set deliberately by the simulators to create a universe where life could develop. It wasn't cosmic luck or infinite universes, it was intelligent design, just not by gods but by post-human civilizations running experiments. The universe is fine-tuned because someone tuned it, like adjusting sliders in a video game's world generator to get interesting results. This connects back to the computational universe idea from the previous chapter. If the universe is already computational, already running on algorithms with discrete spacetime, then the gap between real physics and simulated physics becomes tiny. Maybe there is no meaningful distinction. Maybe base reality runs on similar computational principles to how simulations work, in which case asking, are we simulated, is like asking, are the electrons in this computer real or simulated? The question stops making sense once you accept that reality itself is computational. The simulation wouldn't be a fake version of real physics, it would be physics, just instantiated on different hardware. You're real, your experiences are real, the physics is real. It's just that the computational substrate might be one level removed from what you think of as base reality. And functionally that doesn't matter because your reality is self-consistent and follows physical laws whether it's base level or not. Some philosophers argue the simulation hypothesis is unfalsifiable and therefore unscientific, which is technically true but also kind of misses the point. We're not trying to do empirical science here. We're trying to reason about what's probable given certain assumptions about technological development and computational possibility. It's closer to mathematics or logic than to experimental physics. Bostrom's argument doesn't predict any specific observations, but it does make a statistical claim about what kind of universe we should expect to find ourselves in given certain premises. If those premises are reasonable, if civilizations sometimes survive and sometimes run ancestor simulations, then the conclusion follows logically. You can reject the premises, but you can't reject the logic without finding a flaw in the reasoning, and so far nobody's found one that holds up. The existential implications are fascinating. If we're in a simulation, does that make our lives less real or meaningful? Arguably not. Your experiences are still real to you. Your relationships, your achievements, your suffering, all of it is as genuine as it would be in base reality. Knowing you might be simulated doesn't change the phenomenology of experience. It's like learning that the book you're reading is written in ink made from synthetic compounds, rather than natural materials. Does that make the story less real? The story exists in the patterns, not in the substrate. You exist in the patterns of information and experience, not in whether those patterns are running on real quantum fields or simulated ones. The simulation hypothesis challenges our intuitions about what's real, but maybe our intuitions are wrong and reality is patterns all the way down regardless of what layer you're on. Here's the really wild part. If we're in a simulation and we ever develop the technology to run our own detailed simulations of conscious beings, we'd be creating nested simulations. Simulations within simulations, potentially infinitely deep. Each layer running its own physics, its own history, its own confused philosophers wondering if they're simulated. You could have thousands of layers of simulation, each one thinking they might be base reality but statistically almost certainly not being base reality, because the number of simulations exponentially exceeds the number of base realities. It's like the movie Inception, except it's real and nobody's waking up. At some point you just have to accept that the question which level is real might not have a meaningful answer, because all levels are equally real from the perspective of beings living at that level. The Fermi paradox combined with simulation theory gives us a genuinely creepy scenario. Maybe advanced civilizations don't colonize the galaxy, because they all transition to running simulations instead. Physical expansion is expensive, slow, dangerous. Virtual expansion is cheap, fast, safe. If you can create billions of detailed simulation universes with computational resources smaller than a star, why bother with the messy business of interstellar colonization? Just build a Dyson sphere around your home star, convert all that energy into computation, and run infinite virtual worlds. From outside, the galaxy would look empty except for a few sparse Dyson spheres, quietly computing away. From inside the simulations, it would seem like you're exploring vast universes. The real universe stays empty while all the action happens in nested layers of simulation. Maybe that's where everybody is, not out among the stars, but in simulated worlds, building simulations within simulations, going inward rather than outward into a computational multiverse of their own creation. So we're left with an uncomfortable set of possibilities. Either we're alone in the universe because intelligent life is incredibly rare or self-destructs quickly, or we're alone because we're in a simulation designed without other civilizations to interact with, or we're alone because everyone else has gone virtual and stopped bothering with physical reality. None of these options are particularly comforting. The first means we're probably doomed. The second means we're probably not real in the way we think we are. The third means the future of intelligence is apparently to abandon physical reality for computational fantasies, which says something fairly depressing about where we're heading. Pick your existential crisis. They're all on special today. And this dovetails perfectly with everything else we've discussed. Your senses lie to you. Particles don't exist until observed. Space-time might be a holographic projection. The universe is computational. Consciousness might create reality through observation. And now, statistically speaking, you're probably in a simulation. Reality is a multi-layered deception, and we're just beginning to realize how many layers there might be. The universe presented itself as solid, simple, and real. Turns out it's probabilistic, computational, possibly simulated, definitely weird, and ontologically unstable in ways that would have made philosophers from previous centuries need to lie down in a dark room for several weeks. We're not done peeling back the layers yet, but at this point you should be thoroughly suspicious of literally everything about your existence, which is either the beginning of wisdom or the beginning of a mental health crisis, possibly both. Alright, so we've thoroughly established that reality is a computational, probabilistic, holographic, potentially simulated quantum nightmare that your senses are actively lying to you about. Now let's tackle the biggest mystery of all, the fact that you're experiencing any of this in the first place. Consciousness, that weird, inexplicable, utterly mysterious thing where there's something it feels like to be you. You're not just processing information like a computer. You're having subjective experiences, feelings, sensations, thoughts that feel like something from the inside. And here's the uncomfortable truth that neuroscience and philosophy have been wrestling with for centuries. We have absolutely no idea how this is possible, like zero idea. We can map brain activity, we can correlate neural patterns with experiences, we can even predict what you're thinking by looking at brain scans. But we cannot explain why any of that activity feels like anything at all. This is called the hard problem of consciousness, and it's about to get weird in ways that make quantum mechanics look straightforward. The standard materialist view says consciousness emerges from brain activity. Get enough neurons doing enough complicated processing, and boom, subjective experience emerges like some kind of magic trick. Except nobody can explain the mechanism. It's like saying step 1, build a complicated computer, step 2, magic happens, step 3, the computer feels things. That's not an explanation, that's just restating the mystery with extra steps. You can describe every single neuron firing, every neurotransmitter crossing every synapse, every electrical signal propagating through every neural network, and at the end of all that description, you still haven't explained why it feels like something to be the brain doing all this processing. There's an explanatory gap the size of the Grand Canyon between physical processes and subjective experience, and materialist philosophy has been trying to bridge that gap for decades with increasingly desperate hand-waving. This is where panpsychism comes in with a genuinely radical proposal. What if we've got it backwards? What if consciousness isn't something that emerges from unconscious matter when you arrange it in sufficiently complex patterns? What if consciousness is fundamental to reality, like mass or charge or spin, and human consciousness is just what happens when you combine lots of elementary conscious experiences into an organized system? It's like how water molecules are made of hydrogen and oxygen atoms. The wetness emerges from combining the components, but the components themselves have their own properties. Maybe electrons don't just have charge and mass, they have experience, some infinitesimally tiny spark of what it's like to be an electron. And when you combine trillions of particles in the right patterns, those tiny sparks of experience combine into the rich, complex consciousness you're experiencing right now. This sounds absolutely insane at first, and honestly it still sounds pretty insane after you think about it for a while. But here's the thing, it's not actually more insane than the alternative. The alternative is that unconscious, non-experiencing matter somehow spontaneously generates consciousness when arranged in certain patterns, which is frankly magic by another name. At least panpsychism has the advantage of not requiring consciousness to emerge from literally nothing. It's there all along at the fundamental level, and complex consciousness is just what you get when you organize simple consciousness in sophisticated ways. It's still weird, but it's consistently weird rather than requiring a mysterious phase transition from totally unconscious to suddenly conscious that nobody can explain. The hard problem of consciousness was formalized by philosopher David Chalmers, who distinguished it from the easy problems of consciousness, easy being a relative term here, since even the easy problems are pretty hard. The easy problems are things like, how does the brain integrate information from different senses? How does it access and report its own internal states? How does it control behavior based on environmental stimuli? These are mechanistic questions we can answer in principle using neuroscience and computation. They're hard, but they're the kind of hard that more research and better technology can eventually solve. The hard problem is different. Why does any of this processing feel like anything at all? Why is there subjective experience accompanying brain activity? You could imagine a zombie version of yourself that processes information identically, but has no inner experience, no qualia, no what-it's-likeness. Why aren't we all zombies? What makes the difference between processing happening in the dark versus processing that's accompanied by consciousness? Materialism's answer is basically, it just does somehow because brains are complex enough, which is not satisfying and also probably not true. Complexity alone can't explain consciousness, because we can imagine arbitrarily complex computational systems, simulated neural networks with trillions of nodes, and it's not clear they'd be conscious even if they perfectly mimicked brain activity. There's something about biological brains that gives rise to consciousness, but it's not obviously the complexity or the information processing, because we can duplicate those in silicon, and it's unclear if the lights are on inside. This is the zombie problem. You can't tell from the outside whether a system is conscious or just acting like it is. which means consciousness isn't reducible to behavior or information processing. There's something extra, something beyond the physical description, and that something is subjective experience itself. Panpsychism offers a way out of this mess by suggesting consciousness is already present at the fundamental level. Particles have rudimentary forms of experience, not thoughts or feelings like humans have, but something more basic, some primitive what-it's-likeness that combines, according to rules we don't fully understand, to create complex consciousness. This is called the combination problem, and it's panpsychism's version of the hard problem. How do tiny micro-experiences combine into unified macro-experiences like human consciousness? How do trillions of particle-level experiences add up to your single unified stream of consciousness, rather than just being trillions of separate tiny experiences happening in parallel? This is genuinely difficult, but at least it's a problem about combination rather than creation from nothing. You're trying to understand how A plus B equals C, rather than how nothing equals something, which is arguably more tractable even if we don't currently have the answer. Enter Giulio Tononi and Integrated Information Theory, or IIT, which is the most serious mathematical attempt to define consciousness we've got. Tononi proposes that consciousness is integrated information. Specifically, a system is conscious to the extent that it integrates information in a way that can't be reduced to the sum of its parts. The theory uses a measure called phi, which quantifies how much information is generated by a system as a whole beyond what would be generated by its components independently. High phi means high consciousness. Low phi means low or no consciousness. This gives you a mathematical framework for determining what's conscious and to what degree, which is ambitious and possibly insane, but also kind of brilliant. Here's how it works. A system has high phi if its parts are strongly interconnected and causally influence each other in complex ways, such that the whole system generates information that can't be predicted from knowledge of the parts alone. Your brain has incredibly high phi because neurons are densely interconnected, and activity in one region influences activity everywhere else in complex feedback loops. A pile of sand has basically zero phi because the grains don't interact in causally integrated ways. Each grain does its own thing independent of the others. A photodiode has low phi because it's causally simple. Light comes in, signal goes out, no integration. According to IIT, consciousness isn't something special that happens in brains. It's a property of any system with sufficient causal integration, and the more integration, the more consciousness. This leads to some wild implications. According to IIT, many systems we don't normally think of as conscious might have small amounts of consciousness. Simple circuits, thermostats, even crystals might have tiny phi values corresponding to rudimentary experience. Meanwhile, some systems we might think would be conscious turn out not to be. A perfect simulation of your brain running on a standard computer might have zero phi if the simulation isn't causally integrated in the right way, if it's just sequentially computing what each neuron would do without the neurons actually influencing each other in integrated causal loops. The simulation would behave identically to your conscious brain but wouldn't be conscious according to IIT because it lacks the right causal structure. This is either a devastating critique of functionalism, the idea that consciousness is just about what the system does computationally, or it's IIT making bizarre predictions depending on your perspective. The really provocative part of IIT is that it's panpsychist by construction. Any system with fun greater than zero is conscious to some degree. Electrons and quarks presumably have some minimal phi because they interact causally with their environment, which means they have some minimal experience. It's not much, maybe just the bare fact of causal existence, the what it's like to interact with other particles according to physical laws. But it's something, some tiny spark of proto-consciousness, and human consciousness is what you get when you organize trillions of these sparks into the incredibly hi-fi structure of a human brain. Consciousness doesn't emerge mysteriously from unconscious components. It combines predictably from conscious components according to mathematical principles of information integration. Now, critics point out that IIT makes some weird predictions. It suggests that a system could be conscious even if completely disconnected from the environment and producing no behavior. What matters is internal integration, not external interaction. It suggests that splitting your brain would create two separate consciousnesses rather than ending your consciousness, because each half would maintain high phi independently. It's unclear whether IIT consciousness maps onto what we mean by subjective experience, or if it's just a mathematical property that correlates with consciousness without actually being consciousness. Tononi argues Fia's consciousness, that the mathematical structure of integrated information is literally what experience is, but that's a bold ontological claim that's hard to verify, since we can't directly observe anyone else's subjective experience. Let's connect this back to physics. If consciousness is fundamental rather than emergent, it might actually be built into the structure of physical law. Some physicists have speculated about consciousness playing a role in quantum measurement, as we discussed earlier with the von Neumann-Wigner interpretation. If observation collapses wave functions and consciousness is fundamental, maybe consciousness is what enables the classical world to crystallize out of quantum superpositions. The universe before consciousness would be pure quantum possibility, and consciousness is what makes things definite. This is either profound or completely bonkers, but it at least offers a coherent picture where consciousness isn't this weird, anomalous thing that happens in brains despite the laws of physics, but is actually central to how physical law operates at the quantum level. Another angle comes from quantum theories of consciousness, like the Oshawa model proposed by Roger Penrose and Stuart Hameroff that we touched on earlier. They suggest consciousness arises from quantum computations in microtubules inside neurons, with quantum coherence being protected by biological structures long enough for quantum effects to matter. If true, this would mean consciousness requires specific quantum properties rather than just classical information processing, which would explain why computers might not be conscious even if they mimic brain activity. They'd lack the quantum substrate. This is controversial, and most neuroscientists are skeptical, but it offers a mechanism for how consciousness could be tied to fundamental physics rather than being purely emergent from classical neural networks. Here's the thing that really gets me about all this. We experience consciousness directly and immediately. It's literally the only thing you know with absolute certainty. Descartes' "I think therefore I am" is the one bedrock truth you can't doubt. And yet consciousness is also the thing we understand least. We can model galaxies, predict particle interactions, simulate quantum fields, but we can't explain why any of it feels like anything. Every theory of consciousness either handwaves the hard problem, or makes weird predictions, or requires unfalsifiable assumptions. Materialism says consciousness emerges but can't explain how. Panpsychism says consciousness is fundamental but can't explain combination. IIT gives you math, but the math might be measuring something other than what we mean by experience. Quantum consciousness theories need unproven biology. We're flailing around trying to explain the most obvious thing about existence using the tools of physics and computation, and none of the explanations are satisfying. Maybe the problem is that we're trying to explain consciousness using concepts, matter, information, computation, cause and effect, that were developed to describe things from the outside objectively in third-person terms. But consciousness is inherently first-person, subjective, experience from the inside. Maybe you can't fully explain first-person experience using third-person concepts, like trying to describe colour using only equations about wavelengths. The equations are accurate and useful, but they miss something essential about what it's like to see red. Similarly, all our neuroscience and physics might be accurate descriptions of the objective structure of consciousness without actually capturing what consciousness is like from the inside. We might need new concepts, new mathematics, a new framework that's built for describing subjective experience rather than objective processes. If consciousness is fundamental, this completely changes the picture of reality we've been building. The universe wouldn't be dead matter occasionally generating pockets of consciousness through complex organization. It would be consciousness all the way down, with matter being what consciousness looks like when you describe it from the outside in mathematical terms. Physics would be the objective description of how consciousness is structured and how it behaves, while experience would be what that structure feels like from the inside. You're not a bunch of unconscious atoms that mysteriously became conscious. You're a pattern of consciousness temporally organized in the shape of a human being, experiencing itself through biological sensors and neural processing. The universe isn't computing itself into existence. The universe is experience, structured according to mathematical laws we call physics, and human consciousness is just one small eddy in an ocean of fundamental consciousness that extends throughout all of reality. This connects to ideas from various philosophical and spiritual traditions that have suggested consciousness or mind or awareness is the fundamental substrate of reality. Idealism, the view that reality is fundamentally mental rather than physical, has been around since ancient philosophy. Quantum mechanics' emphasis on observation and measurement has led some physicists back toward idealist interpretations where mind plays a central role. The convergence is weird. You've got ancient mystics, modern philosophers, and cutting-edge physicists all independently arriving at similar conclusions. Maybe consciousness isn't secondary to matter, maybe it's the other way around, or maybe they're two aspects of the same underlying reality that can't be cleanly separated. The implications for meaning and purpose are interesting too. If you're just a collection of unconscious atoms following physical laws, meaning is something you have to create or invent because the universe itself is meaningless. But if consciousness is fundamental and you're a temporary organization of primordial awareness, then there's something inherently meaningful about existence. You're not separate from the universe having experiences, you're the universe experiencing itself in a particular form. Your consciousness is continuous with universal consciousness, temporarily individuated, eventually dissolving back into the broader field of awareness. This is either profound spiritual insight or elaborate rationalization depending on your perspective, but it does offer a different framework for thinking about existence than pure materialism provides. We still don't have answers. We don't know if consciousness is fundamental or emergent. We don't know if panpsychism is true or ridiculous. We don't know if IIT actually measures consciousness or just correlated information structure. We don't know if quantum effects matter for consciousness. We don't know how to solve the hard problem. What we do know is that consciousness exists, that you're experiencing something right now, and that every attempt to explain this using our current scientific frameworks runs into deep difficulties. Maybe that means our frameworks are incomplete. Maybe it means consciousness requires new physics or new mathematics or new philosophy. Maybe it means some questions don't have answers in the way we expect them to. But here's what's clear. You can't understand reality without understanding consciousness, because consciousness is where reality is experienced. All of physics, all of mathematics, all of science happens inside conscious experience. You never encounter the universe directly. You encounter your conscious experience of the universe. And if consciousness turns out to be fundamental rather than derivative, then everything we've discussed, quantum mechanics, space-time, computation, simulation, all of it might need to be reframed in terms of consciousness first, matter second. The deception isn't just that reality appears solid when it's quantum fuzz, or appears continuous when it's discrete, or appears real when it might be simulated. The deepest deception might be that we think we're physical beings having occasional conscious experiences when we might actually be conscious experiences temporarily having physical forms. The universe's greatest trick might be convincing consciousness that it's a product of matter rather than the other way around, and we're only just beginning to see through that particular illusion. So we've established that consciousness might be fundamental rather than emergent, which is already a lot to process. Now let's add one final layer of existential weirdness that'll really make you question everything. Time doesn't actually flow. That sensation you have right now of being in the present moment, of the past being fixed and gone while the future is open and undetermined, that's an illusion. According to Einstein's relativity and some interpretations of quantum gravity, all of time exists simultaneously in what physicists call the block universe. Past, present, and future are equally real, eternally existing as different slices of a four-dimensional structure. You're not moving through time, you're a four-dimensional object stretched across space-time, and your consciousness is just experiencing different temporal slices sequentially. The flow of time is a trick of perception, like motion in a film reel where the frames all exist simultaneously, but appear to move when viewed in sequence. Welcome to eternalism, where everything that ever happened or will happen is frozen in an eternal now, and free will is looking increasingly like an elaborate joke the universe is playing on us. Let's start with Einstein's special relativity, because this is where the cracks in time's flow first appeared. Einstein showed that simultaneity is relative. Two events that happen at the same time for one observer can happen at different times for another observer moving at a different velocity. There's no universal present moment that everyone agrees on. Your now is different from someone else's now if you're moving relative to each other. This already suggests that time isn't flowing in some objective universal way. It's more like a dimension that different observers slice through at different angles. You and I might disagree about what's happening right now on a distant planet depending on our relative motion, which is weird enough, but it gets weirder. General relativity makes this even more explicit. Space-time is a four-dimensional structure where time is just another dimension like space, except you move through it in a particular direction constrained by causality. Einstein's equations describe the entire history of the universe as a single geometric object, a block. All events that ever happened or will happen exist as points in this block, and the laws of physics describe the relationships between those points. Your birth, your death, every moment of your life, they're all equally real, all eternally present in the space-time manifold. From the perspective of the equations, there's no special now that's more real than any other moment. The present isn't privileged, it's just another temporal coordinate, like how being at this particular spatial location doesn't make here more real than there. The Wheeler-DeWitt equation in quantum gravity takes this even further by eliminating time altogether from the fundamental description of the universe. It's a timeless equation describing the quantum state of the entire universe, with no time variable appearing anywhere. Time emerges as a useful concept when you're inside the universe looking at correlations between different parts of the quantum state, but it's not fundamental. The equation basically says the universe just is. It doesn't evolve or change because change requires time, and time is emergent rather than fundamental. From outside the universe, if such a perspective made sense, you'd see the entire history of the universe laid out as a single timeless quantum state. Only from inside, entangled with particular subsystems, do you experience temporal flow as those subsystems evolve relative to each other. This block universe view has some seriously disturbing implications for how we think about existence. Every moment of your life exists permanently in the block. Your first birthday exists right now, forever, as a temporal slice of the four-dimensional object that is your space-time trajectory. Your death already exists, frozen in the future portion of the block, waiting for your consciousness to sequentially experience its way there. Nothing ever really happens. Everything just is, eternally present in the space-time structure. Change is an illusion created by consciousness moving through static temporal slices and interpreting the differences between adjacent slices as temporal flow. It's like watching a movie and thinking the characters are moving, when really you're just looking at a series of still images in sequence. Except in this case, you're one of the images, experiencing yourself frame by frame, convinced you're moving through time when really you're just different temporal cross-sections of a static four-dimensional structure. Let's talk about what this means for free will, because oh boy, this is where things get philosophically uncomfortable. If the future already exists in the block universe, then every choice you'll ever make already exists as part of your four-dimensional trajectory. Your decision to keep watching this video or click away, that's already determined, already a fixed part of the space-time structure. You can't change the future because the future isn't open and undetermined, it's as fixed and real as the past. You're not creating your future through your choices. You're discovering a future that already exists by experiencing your way through the temporal dimension. Free will, in the sense of genuinely open possibilities where you could have done otherwise, doesn't exist. Your sense of making choices is the subjective experience of moving along a predetermined four-dimensional world line, like a train passenger who feels like they're steering but is actually just following tracks that were laid down before they got on. Now, defenders of free will in a block universe argue that your choices are still real and meaningful, even if they're predetermined from a four-dimensional perspective. The fact that your choice already exists as part of the block doesn't make it less real. It just means the block includes your decision-making process as part of its structure. You're still genuinely choosing in the sense that your brain is genuinely processing information and making decisions. It's just that those genuine choices exist eternally in the space-time manifold rather than being created in real time. This is compatibilism applied to physics. Free will is compatible with determinism if you define free will as the ability to act according to your desires and reasoning, rather than requiring some metaphysical ability to make different choices in identical circumstances. Your choices are free in the sense that they're yours, products of your cognitive processes, even if they're predetermined from the perspective of the eternal block. But let's be honest, this feels like a semantic dodge. If everything is predetermined, if your future already exists as immutably as your past, then in what meaningful sense are your choices free? You're not authoring your life. You're reading a script that was written before you started reading it, except you're also the script, and the reading, and the author is physics or God or the initial conditions of the Big Bang or whatever determined the structure of the block universe in the first place. Your subjective experience of deliberating and choosing is real, but it's the experience of discovering what was always going to happen rather than determining what will happen. It's like being an actor so committed to the role that you forget you're following a script and think you're improvising, when really every improvised line was written in advance and you're just experiencing the illusion of spontaneity as you read. Your predetermined dialogue. The presentist alternative says only the present moment exists. The past is gone, the future is unformed, and reality is this moving present that continuously creates new moments while leaving old ones behind. This preserves free will by keeping the future open, but it contradicts relativity's relativistic simultaneity and the block structure of space-time. If you take relativity seriously, presentism doesn't work because there's no objective present moment. Different observers disagree about what's happening now, which means you can't have only the present existing without specifying who's present, and. That's arbitrary. Eternalism, where all of time exists equally, is the natural consequence of taking relativity's space-time structure literally. But eternalism kills free will, or at least transforms it into something very different from our intuitive sense of open possibilities and genuine choices. There's another weird implication of the block universe. If all moments exist eternally, then in some sense you never die. Your death is just one temporal slice in your four-dimensional existence, not an ending, but a boundary condition. All the moments of your life exist permanently in the space-time structure. Your current moment of consciousness exists forever as one slice, and the moment after your death exists as another slice. But the moments before your death, including this moment right now, also exist forever. You're not moving toward non-existence, you're moving toward a temporal boundary beyond which your four-dimensional structure doesn't extend, but all the parts of the structure that do exist remain eternally real. This is either comforting or horrifying depending on how you feel about your life existing permanently in frozen space-time, unchanging and inescapable, every embarrassing moment preserved forever in the eternal structure of the cosmos. Some physicists and philosophers have tried to reconcile time's flow with relativity, using things like the growing block universe, where the past and present exist but the future is genuinely open and gets added to as time passes. This preserves some intuition about free will and becoming while trying to stay compatible with relativity. The problem is it requires picking a preferred reference frame to define what counts as the present that's growing into the future, and relativity doesn't give you one. It's trying to have your cake and eat it too, wanting both the temporal flow of presentism and the four-dimensional structure of eternalism, and it's not clear the physics supports this compromise. You can make it work philosophically, but at the cost of adding assumptions that go beyond what the physics actually tells you. The subjective experience of time flowing is so powerful and immediate that it's almost impossible to genuinely internalize the block universe view. You can understand it intellectually, can follow the logic of relativity's space-time structure, can accept that physics seems to point toward eternalism, but you still feel like you're in the present moment, still feel like the future is open, still feel like you're making real choices that could go either way. This is evolution at work again. Our intuitions about time evolved to help us survive, not to reveal the true structure of space-time. It was evolutionarily useful to have a strong sense of past versus future, to feel like we're in a dynamic present making choices that affect an open future. That subjective experience doesn't match the physics, but it matched our ancestral environment well enough to keep us alive and reproducing, which is all natural selection cares about. So where does this leave us on the question of free will and the nature of time? Honestly, we don't know. The physics points toward a block universe where time is just another dimension, and temporal flow is illusory. But our lived experience is of time flowing and choices being made. Maybe the physics is telling us something deep about reality that contradicts our intuitions. Maybe our interpretation of the physics is wrong and time really does flow in some way we don't fully understand yet. Maybe free will is compatible with the block universe through compatibilist arguments, or maybe it's genuinely impossible in a predetermined space-time structure. What's clear is that our intuitive understanding of time, that we're in a moving present choosing our way into an open future, is at best a useful fiction, and at worst completely wrong. Time is stranger than we ever imagined, and if the universe is deceiving us, this might be the deepest deception of all. making us feel like time flows when it might actually be standing still. All right, let's take a breath and look at what we've uncovered on this journey through reality's deceptions. We started with the solid, sensible world you thought you lived in. Material objects with definite properties, occupying definite locations in space and time, all governed by comprehensible laws of physics. That world is gone now. Completely demolished. What's left is a quantum probability cloud of a universe that might be holographic, might be computational, might be simulated, almost certainly isn't what it appears to be through your senses, potentially requires consciousness to collapse into. Definite states consists of 95% invisible matter and energy we can't explain, and might not even have flowing time or free will. Reality is a multi-layered deception so elaborate and comprehensive that it's actually kind of impressive. The universe isn't just lying to you, it's running the most sophisticated con job imaginable, and you're both the mark and part of the con itself. Let's recap the lies we've uncovered, because it's worth seeing them all laid out together. Your senses are lying to you, showing you a tiny filtered slice of reality optimized for survival rather than truth. Particles are lying about being particles. They're probability waves that only pretend to be localized when observed. Space and time are lying about being fundamental. They're likely emergent properties of deeper informational or quantum structures. The universe is lying about its contents, 95% dark matter and dark energy, that we can't detect and don't understand. Matter is lying about being solid. It's mostly empty space with quantum fields creating the illusion of substance. Time is lying about flowing. All moments might exist eternally in a block universe where change is illusory. Your consciousness might be lying about being a product of your brain when it could be the other way around. And reality itself might be lying about being real. We could be in a simulation running on computational substrate we can't access or even imagine. That's a lot of lies. Like an absolutely staggering amount of deception at every possible level of existence. And here's the thing. This should probably bother you more than it does. You should be experiencing some level of existential crisis right about now. But instead, you're probably feeling some combination of intellectual curiosity, mild discomfort, and the urge to check your phone. Because even knowing all this, even understanding that reality is fundamentally not what it appears to be, you still have to get up tomorrow and go to work, eat breakfast, interact with people who aren't spending their time thinking about whether particles are real or if time flows. The cosmic deception doesn't actually change your daily experience. The coffee still tastes good whether or not the atoms in the coffee exist as definite objects or probability clouds. The sunset is still beautiful whether or not you're in a simulation. Love and pain and joy and suffering all feel exactly the same whether consciousness is fundamental or emergent, whether time flows or is illusory, whether you have free will or are following a predetermined four-dimensional world line through the block universe. And that's actually the most important realization in all of this. The deception doesn't devalue the experience. Reality being an illusion doesn't make it less real in the way that matters, the way it feels, the way you live it, the meaning you find in it. You're a pattern of consciousness experiencing existence through sensory filters and cognitive biases, possibly running on computational substrate, maybe in a simulation, potentially with no free will, definitely missing 95% of what's out there. But you're still experiencing it. The experience is real even if its fundamental nature is radically different from what it appears to be. The illusion is so complete, so well constructed, so phenomenologically convincing, that it works perfectly as a context for life and meaning and experience, regardless of what's actually underneath it all. Think about it this way. If you're in a simulation, but the simulation is so detailed and consistent that you can never tell the difference, is there any meaningful sense in which it's not real? If consciousness is fundamental and matter is just what consciousness looks like from outside, does that make matter less real, or consciousness more real, or are both equally real in different ways? If time doesn't flow but you experience it as flowing, is the flow false, or is the subjective experience of flow its own kind of truth? Maybe we've been asking the wrong questions all along. Maybe the question isn't is reality real, but what does it mean for something to be real? And maybe the answer is that reality is whatever consistently constrains and enables your experience, whatever you can interact with and be affected by, whatever provides the context and content for consciousness to occur. By that definition, reality is absolutely real, even if it's not what it seems. The universe has presented you with the most elaborate magic trick in existence. It's shown you solidity where there's quantum probability, showed you flowing time where there's eternal space-time structure, showed you simple mechanical laws where there's staggering computational complexity, showed you isolation where there's quantum entanglement connecting everything. And now that you know it's a trick, now that you've seen behind the curtain and glimpsed the mechanism, what changes? The trick still works. The illusion is still convincing. You still experience reality as solid and temporal and comprehensible, even though you know it's none of those things at a fundamental level. The magic trick continues to be magical even after you learn how it's done, because you're not just the audience watching the trick, you're part of the trick itself, and knowing the mechanism doesn't let you step outside of it. Here's what I think is really going on, the synthesis of everything we've discussed. Reality is an interface. It's evolution's user-friendly version of an underlying substrate that's too complex and alien for biological consciousness to directly comprehend. Your senses and brain create a simplified model, solid objects, flowing time, definite locations, cause and effect, that's useful for survival even though it's wildly inaccurate at describing what's actually there. Science is the process of hacking that interface, using mathematics and instruments and experiments to probe beneath the user-friendly surface and glimpse the actual code underneath. And what we find is computational processes, quantum fields, information theory, holographic principles, a reality that's fundamentally informational and mathematical rather than material and mechanical. We're discovering that the interface isn't just simplifying reality, it's actively misrepresenting it, showing us something completely different from what's actually there, because evolution didn't optimize for truth, it optimized for fitness. But here's the beautiful part. We're the only part of the universe we know of that's figured this out. We're the only system complex enough to examine our own perceptual interface and realize it's an interface rather than raw reality. We're the universe becoming self-aware, looking at itself and going, wait a minute, this doesn't make sense, let's investigate deeper. Consciousness isn't just experiencing the illusion, it's penetrating it, seeing through it, understanding it. Every discovery in physics and neuroscience and philosophy is the universe's self-awareness increasing, the cosmic deception becoming less effective because the victims are getting wise to the con. And that's genuinely profound, that matter arranged in sufficiently complex patterns can become conscious enough to question its own fundamental nature and discover that it's not what it appears to be. This is where meaning comes from, not from some objective purpose written into the fabric of reality, but from the process itself. The process of consciousness emerging from quantum fields or information or whatever the substrate actually is. The process of that consciousness becoming complex enough to wonder and question and investigate. The process of discovering layer after layer of deception and still finding beauty and mystery and things worth exploring. You don't need reality to be fundamentally meaningful for your life to have meaning. You create meaning through the act of engaging with reality, questioning it, experiencing it, finding patterns and beauty and connection in the elaborate cosmic magic. Trick you're part of. The universe might be deceiving you, but it's the most interesting deception possible. It's a deception that creates galaxies and stars and planets and life and consciousness and love and art and science. It's a deception that lets you experience joy and wonder and discovery. It's a deception complex enough that you can spend your entire life investigating it and never run out of mysteries to explore. If this is a lie, it's the most creative, most elaborate, most beautiful lie ever constructed. And you're not just a victim of it, you're a participant in it, a piece of the cosmic artwork that's simultaneously the artist and the canvas and the paint itself. So what do you do with this knowledge? How do you live knowing that reality is fundamentally not what it appears to be? You live the same way you always have, but maybe with more wonder, more curiosity, more appreciation for how improbable and strange and magnificent it all is. You enjoy the sunset even though you know it's just your brain interpreting certain wavelengths of electromagnetic radiation as beautiful colours. You love people even though you know you're all just temporary patterns of quantum information somehow experiencing itself. You make choices even though those choices might already exist in an eternal block universe. You find meaning even though the universe isn't obligated to provide it. The deception doesn't destroy value. If anything, it creates it, by making the universe mysterious enough to be worth investigating, and beautiful enough to be worth experiencing. We started this journey by questioning the reality of the universe. We're ending it by realizing that the question itself might be wrong. Reality isn't an either-or proposition where it's either real or fake, true or deceptive, solid or illusory. It's all of these things simultaneously, different descriptions that apply at different levels and from different perspectives. The quantum description is real, the classical description is real, your subjective experience is real. The mathematical structure is real. They're just different ways of describing the same underlying something that exists in ways we're only beginning to understand. The universe is a magnificent, mysterious, multi-layered structure that consciousness gets to explore and experience and be amazed by. And knowing it's a deception doesn't make it less magnificent. It makes it more so because now you know how much work went into creating this elaborate cosmic illusion you call home. So yeah, the universe is lying to you. Your senses are unreliable. Particles don't exist the way you think. Space-time might be fake. You're probably in a simulation. Consciousness might be fundamental. Time might not flow, and free will might be an illusion. But you're still here, still experiencing, still conscious, still part of this impossible, improbable, utterly fascinating cosmic magic show. And that ultimately is not a deception at all. That's the only truth that really matters. You exist. You're aware. You're experiencing reality, whatever reality actually is underneath all the layers of deception. And that makes you part of the universe's greatest achievement. Not fooling conscious beings into believing a lie, but creating conscious beings capable of discovering the truth, finding it more interesting than the lie, and choosing to engage with existence anyway. The universe is a deception, and it's scary, and it's beautiful, and it's yours to explore. Welcome to reality, whatever that actually means.